Yes, well, Radek. We have just started the broadcast, right? So
Hmm?
from now, people can see us, and I hope they can hear us for sure. The the webinar is being recorded from now, so
Okay.
it's recording, and there's a new client, right? Of
Hmm.
this, and it says we have 59 minutes only, so I hope it's not gonna be terminated.
Cut off.
In,
Okay.
right? It scares me a little bit. Why there's the 59 minutes remaining only?
Yeah, because you said it for one, right? 1 hour.
And
But
do
I
you think
you
it's
can stop the timer if you click on the
can we click it?
time window.
Stop timer. Okay. So
You can hide it. You can stop it. So I
hide
think
timer
it's
from
just
attendees so they can see it. You think they can see it?
yeah.
It
I
seems
think
they can
so.
see it. So let's hide it because no one says
We
here
don't.
it's gonna be just 1 hour. I will mention it in the beginning. So
Hmm.
I'm hiding the timer. And what else? And also we can Radek, do you think we should stop it or pause it?
I don't think so.
Like
I
pause it?
don't think so.
It's not gonna terminate us, right? It would be
I think it's just
so
informative
and
to.
it's just a timer. Okay. Okay, let's keep it. Let's risk it, right? This way.
At least I hope so.
Yeah, yeah. Yeah, okay. So, well. I think it's on my clock. It's 2 p.m. So it's actually time to start the webinar. So, what do you think, Radek?
Yes, let's go for it.
We have quite some people already here. So, yeah,
Nice.
okay. I guess it has to start. So let's start it.
Yeah.
So, yeah. And how to what to? No, I just minimize this and okay. So let's
Yeah,
start
I
the
can
webinar.
see. Yeah, I can see the presentation now. So
Okay. Well. Okay. So, hello everyone. This is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar, which is about CFD preprocessing. It's a special format. In today's webinar, we would like to dedicate our all the time just exclusively to preprocessing. Which means it's a preprocessing for us is preparing the geometry for CFD simulation. It's just preparing the geometry. So we'll be talking about how to open the geometry, how to access it, how to split it, how to clean it, and to be simulation ready for CFD. How we think it's useful, efficient, and accurate. So there will be another webinars for CFD simulation and also meshing. So today's webinar is not about meshing. Meshing will be sometimes else, but it will be about preprocessing, just preparing the geometry. There are multiple ways, so let's take a look at it. And yeah, so preprocessing. Yeah, so the webinar is being recorded, and the recording, yes, it will be later publicly available on our YouTube channel. So feel free to follow later on your leisure time, and you can break it into sessions if you particularly like something or need to review it or see it again. Okay, so the webinar is going to take perhaps more than 1 hour because we have a lot of things prepared and we have been preparing for this webinar quite a lot. So it will take yeah quite some time. I don't promise anything, and yeah, there will be couple of sessions. Let me do last check that everything works. The day with me is Radek here as usual. So hello Radek, can you see us? Can you hear us?
yes, hello Luboš, and hello all the audience. Yeah, I can see you. I can hear you. All of us
Yes.
in a good mood. I hope so.
Yeah.
Let's
Let's
go
make
for
it.
it.
Yeah. We're happy to show things as usual. So okay, so it seems everything is working. And Radek, I suggest we would switch the cameras off for now, and we will come back at the end if ever. Yeah, I mean
Okay.
on the
Yeah,
screen.
sure.
Yeah, so let's switch the cameras off for now. Yeah, so this makes, I guess, the screen ratio even better, because there will be details. I'm sure that it will be very interesting to follow. So yeah. Let's go ahead. Let's make it. So here is the agenda of today's webinar. So there will be, yeah, we have to undergo a necessary introduction. I will take care that it will take less than 5 minutes. If it will take more, I will personally buy you a beer when we meet sometime next time. So yeah, 5 minutes introduction. It's necessary. We have to say what's on the table. Then we will start with general thoughts. We want to repeat or mention the general principles, how we think, and what's necessary, what we need to do. And then we will go more a little bit to details. What are goals? What are principles? And what's the way of thinking when we create the simulation ready geometry? So Radek will show us and tell us a couple of goals and principles. What's required from a proper and professional preprocessing. And then we have a couple of cases to show. So we have, in the first case, we will show what could be an ideal geometry for CFD simulations. So we will show it. Then we have one little case in Blender, how the geometry can be operated. Then we have also an example how everything can be automated with, for example, with CF Turbo. And in the last and perhaps the biggest case, we have a complete process of cleaning and creating the geometry in Salome. It will be Kaplan turbine, and it will be I would say comprehensive process. You start with dirty something, and you end up with simulation ready geometry, and we will explain everything pretty much in detail. Yep. Then at the end of the webinar, as usual, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. I'm sure there is a window. You can ask your questions there. And please ask your questions. It's your time, and it's definitely about you, not about us. So ask, and we will answer your questions, and we will answer all of them. So the most relevant and representative questions will be answered right away here in the webinar. Specific questions which are difficult to take anything away of it for the rest of the audience, we will answer them later via email. But all the questions will be answered, and that will be it. And I guess it sounds like a plan, and let's see what we can do with it. So yeah, I really mean it. I'll do in 5 minutes what I promise. I'll say the necessary introduction. I'm starting the timer on my clock, and let's take a look. So there will be other webinars. The next webinar will be CFD simulation setup, and there we will explain how we approach the meshing and how we approach all the boundary conditions and models and everything. So the next webinar is CFD simulation setup, and the other webinar will be CFD post-processing. So there we will show how to post-process and how to view the results. Again, very interesting topic. So it's basically it's series dedicated to each I would say workflow step. Okay, so those are new webinars, and here we go with the couple of introduction of ourselves. So I guess you know, but still I have to say it. We are CFD Support. It's the company name. We are located in Prague, Czech Republic. We were founded in 2009. And we deal with CFD, FEA, and FSI simulations. We do quite a lot of optimization and also acoustic simulations. We are a relatively small team, but very efficient. And we also developed software, which is called TCAE. And And yeah, most of projects and everything what we do, basically we do in TCAE. We believe it's fantastic software because it's based on open source. It has several software modules, and these software modules communicate with each other and are very efficient because they were designed from scratch to be flexible, to fit any engineering workflow, to be ready for a high level of automation, to be usable in every way. It's not limited on the users' job scores or hardware installations, so the users can be sure that they can use their resources to the fullest. And there's wide range of possibilities how to use it, and yeah, workflow scenarios. It's based on open source, and it consists of more than 60 open source packages. And on top of these open source packages, we have developed more than 50 many years of consistent development in a team, which makes TCAE pretty comprehensive, usable, and ready for the usage in the industry. It's focused, it's automated, it's ready for remote computing, it's ready for computing on desktop, PC, laptop, cloud, cluster, remote computing in Windows or in Linux, in batch mode or in graphical interface. So there's really a wide range of usage. And it's been for like 15 years, it's been tested almost every day on benchmarks. There are more than 50 existing tutorials which are based on real projects we did in the past. And also we have unlimited technical support to ensure that the use of TCAE is smooth, and it brings the value which is enormous. The current release is 25.03. We released new TCAE, new versions every like 6 months. And for the future, we are definitely focusing on optimization. We believe it's the future. We also do quite a lot of acoustics, and it's it's a good spot because not everybody can do that. It's quite complex. And also we focus on the new features, especially new software modules. We are currently developing new software module called T-Base, which is something which allows the users to create to store all the results forever in special databases, to offer to play with the data and create own surrogate models, which is what we believe in. Yes, we also have the TCAE Lite version for those who have no or low budgets. And my timer shows me that time is almost up, and because I like drinking, but still I promised I will finish in 5 minutes, which is happening right now in 5 seconds. So this was the necessary introduction as promised. And let me see. Yeah, let's go ahead with general thoughts. So Radek, still alive?
Yeah.
Did you make
Listening and following.
Okay, that's great. So listen, I think this could be like just a few minutes of joint conversation uh, about general thoughts on the CFD preprocessing. And as promised, I wanted to start with something which is more general, to start with general principles, and then go more and more into the details, right? And of course, I have some thoughts, but if I ask you now, what comes to your mind or on your mind when you hear CFD preprocessing?
Yeah, I imagine that this is the first step the engineer must do before going for CFD simulation, right? Because without geometry, you have nothing to simulate. So you have to have the geometry, the input geometry, and the quality, the formats of the input geometry can cover very wide range of all the formats, quality, details in the geometry, and so on. The source of the model, if it comes from some civil engineer or it comes from a general designer, and this makes the process really complex. And to master CFD workflow, you have to also master the preprocessing, right? You need to prepare the geometry in a proper format with a proper quality, etc. And the engineer needs to know what they expect from the CFD simulation. So what details should be included, what details should be excluded to make the workflow simpler, etc., etc. Right. So what I would say that it is the first step in the process, and it's complex, and uh, some basic rules must be followed to have a good input data for CFD
Yeah.
simulation for the
Yeah.
machine.
Yeah.
Yeah.
From my thank you, Radek. From my side, it's kind of yes, as you mentioned, it's a complex part of the workflow, and it's somehow it's for many users and engineers it's a bottleneck, right? Because
Mm-hmm.
it's
Mm-hmm.
there's a lot of
Agree.
complexity involved in the beginning. There are a lot of various inputs, right? And we have to make the inputs to behave nicely, right? To be like to some level they have to be generic, to be
Yeah.
usable in and automatable, right? So
Mm-hmm.
the mess is caused by the complexity of 3D space, right? Because everything is 3D and there are various formats, right? There are for example parametric models, there are step files, there are CAD files, there are like reduced geometries or the low level geometries like
Mm-hmm.
scans and STL surfaces, and it's quite a mess, right? And there is no measure of quality, right? You have to create your own scale of quality, and that's why quite a lot of experience is involved. Serious amount of skills and knowledge is necessary, I would say, and a lot of complexity is involved. What's very important to say in the beginning that is it's sometimes we say garbage in, garbage out, right? I hope it's
Mm-hmm.
clean. It's
Yeah.
clear what it means. Uh, if you provide if you do bad engineering or poor engineering in the CFD processing, it can be hardly compensated later in the process, right? If
Exactly. Yeah.
poor engineering in the beginning leads to I would say okay, pre-processing sets all the expectations, all the potential and the expectation of accuracy and quality of the results, and it cannot be uh, laterly enhanced or taken back. It's really the first step. It's the foundation of everything, and that's why it's so important, because the foundations the foundation should be solid, should be pretty good, and that may be tricky sometimes.
Yeah.
Uh,
Exactly.
yeah. So we have to. It certainly deserves a lot of attention in the beginning, and it pays off later during the process. And the rest of the process, and I'm a little bit ahead, but the CFD setup is pretty much all the time the same, right? Because
Mhm.
creating the mesh is just the process, but everybody can learn it. CFD
Yes. Yes.
simulation setup is perhaps the simplest part of the workflow, because there are certain rules, you just follow them. There are things you can do or you can't do, you're allowed to do or not allowed to do, but it's a simple process, easy to explain. And post processing is it's again a routine. Of course, everything is very complex, but CFD pre-processing is bottleneck because of the complexity of the data, of the nature of the data, and also of the format of the data, right? That's why it sometimes brings issues. I would I think we can finish this session with good
Mm-hmm.
news that pretty
Yeah.
everything is automatable. Anything can be automated. Anything can be learned with experience. You can very soon or eventually get much better in everything. So everything is difficult in the beginning, but after some time it gets easier, or it can be completely automated. So the good news is everybody can get there after some effort.
Perfect.
So those are general thoughts that comes to our minds, and now I would ask Radek if you can say a little bit more, I would say level 1 details about what are the goals of preprocessing if when it's done properly, what are the basic principles, and what's the component thinking, etc., etc. So
Yeah.
I think you could uh, I'll make you presenter. Yes, there's new content.
Perfect. Okay, let me know when when you can see my
I can
screen.
see your screen. I can see your screen.
Okay, perfect. So can you see the presentation, right?
Yes.
At the moment.
Yes.
Perfect. Okay, so we will continue. So we will go from more general information to more detailed information about the input requirements. So we will mention several rules which has to be followed, and you need to think about them when you start preparing the inputs and or processing your geometry. So this is the list of the main issues and the main principles which you have to follow. So first one is that for CFD simulation, of course, you need the flow path geometry. So typically, if you get the geometry from the designers, which are not CFD engineers, and the design was not uh, um, exported for CFD purposes, but for general purposes, just for manufacturing or any other goals, then the model includes all the details, and many of the details you don't need to include into the CFD geometry. So first is the extraction of the flow path geometry, so only the part of the geometry which touches the fluid and which will be defining your CFD computational domain. The second rule is it must be as simple as possible. So as simple as possible gives you the freedom of simple workflow. Simpler shape will give you better meshing, etc., etc. So typically here, CFD engineering needs to know what is important for the goals for the CFD parameters, output parameters, and needs to decide which part should be cleaned, which part should be simplified to obtain a nice mesh and to obtain a good CFD result and accurate results with respect to the original shape of the geometry. Then to design the CFD domain in general, so including the turbo machinery designs where some part is rotating, some part is not rotating, or including porous media regions or any other kind of physics which should be included into the domain. We design the structure of creating the CFD domain by the component thinking. So it's like Lego, which has to put all the pieces together, but each piece, each component consists of another parts, which will stand for defining boundary conditions, connecting of two components or two regions, etc. So this brings me to the physical boundaries. We need to connect, we need to split each part into the physical boundaries, because on that boundaries, the boundary conditions are prescribed. Different boundary conditions can be defined, or with different parameters can be set, like rough walls or rotating walls, or different temperatures at the different parts of the walls, etc. From the quality point of view, we need to have the watertight property, because the fluid cannot go out where we don't need it to get out. And from the meshing purposes, the mesh domain should be closed. Otherwise, the meshing procedure can collapse, and you don't get any useful mesh. And final, for the STL generation, the triangulation refinement is also important, because this is the first discretization of your smooth smooth geometry shape. So let me quickly go step by step. So I think the flow path geometry's definition is pretty obvious. So typically, if you get from your designer the CAD model of your domain with all the solids, all the parts, all the screws, even engines, and etc. So you need to extract just the inner part, the wetted part of your flow domain where the fluid goes and where the fluid works. So this is the wet surface. This I think is clear. The second part is to make the model as simple as possible. So typically, if you get a general model, in this case of the small vertical Kaplan turbine, so you need to get rid of all the screws of the parts of the all the parts which are outside of the fluid domain, get rid of all the solids, etc., to export a nice fluid domain with only parts which are creating the fluid domain. Then you can focus on the details, typically the connection of the shaft or some bearings or some gaps, which has to be included into the real model, but can bring a lot of troubles with meshing, and maybe those details does not affect the flow parameters too much. So you can exclude them. So if there are some connection bearings with some small gaps which should be problematic to solve, and some leakages or gaps are used for example cooling the system, and you don't need to compute the cooling, you can fix them, you can simplify them too, and replace them with a simple shapes of, for example, here the shaft connection to the stator part. So all the details are important, and the CFD engineer who prepares the geometry should think about this. So this is the simplicity. Then we have the component thinkings. So in the real world, and typically the turbo machine world, but also the external aerodynamics, like for the wind turbines or even the propellers, drones, etc. There are two main domains which we recognize as the stators and rotors. And from the CFD point of view, to connect the rotating and non-rotating parts, we need to define the domains for which we can define the rotation, and for the other parts we can define just the static treatment. So the components basically consist of the stators and rotors, and the additional advantage that the stator parts like the ducts, etc., we can split to another component splitting for several stators, and always at the interfaces automatical evaluation of all the integral values are done. So this gives you a freedom. Then automatically, if you create it this way, you will get all the information on, for example, on the interfaces. So what does it mean, component thinking? So if you have nice cleaned geometry, so we have the wet surface with the inlet and outlets. So we need to split the domain into the rotating and stator parts. For example, we can split the domain into rotors, into the spiral part, outlet parts, outlet extensions, inlet piping, inlet extensions. So typically the CFD workflow likes extended inlets and outlets, so to make the fluid calm, or to simulate the proper inlet distribution of the velocities. So these extensions are necessary, but for example, the measurement are done just before the wheel and right behind the spiral. So we can create also the additional splitting of these duct systems, inlet outlets, etc., to make the puzzle from your turbo machinery and have defined the separate parts of your design. So which puts at the end together will create again all your flow domain, but in addition to the original CAD, it also includes the inlets, outlets, and the interfaces between the neighboring component. So this This we mean under component thinking. And for example, if I go to the TCAE, so it looks like this. So this is, for example, geometry of another Kaplan turbine. So this is the inlet, this is the rotor part and the draft tube. And again, so we have these three components. On the green part, we have the rotor part, so this will be defined as the rotating part, and the other parts will be the stators. And what I will mention in the next slide is that each part of the components is meshed as a separate mesh. So this simplifies the process of the meshing, that you can focus just on the each part, on the each component. And for each component, you will define a special boundary. So from the preprocessing point of view, you need to split the surface of this component into the several parts to be able to define what is the inlet, what is the interface, what are the rotating parts, what are the stationary parts. So again, back to the workflow, this means that your input geometry, for example, if you go for this inlet part or the guide component with the guide vanes, so it basically includes the restial with the inlet, or the geometry part with the inlet, the part with the outlet from the component, blade geometries. So then you can define different mesh refinement. So this is also useful to have more more splits in your geometry, because then you can define high level of refinement on the guide vanes, for example, different level on the hub, and for example, rougher refinement on the stay. So this is the meaning of splitting the component into the additional parts, from which in the final mesh, from which the patches will be created, and on patches you can then define different boundary conditions and, for example, apply special treatment. So this is the physical boundaries. And including this splitting, we have to mention the interface alignment, because the splitting into the component requires the connection between the components, and these connections we call the interfaces. So basically, each component has the interface which can be connected to the neighboring interface, and this interface alignment matches perfectly. So you need to have a perfect match to have a good accuracy of the mapping or interpolating values from one side of the component to the other side of neighboring component. So this is the interface alignment. So you need to, additionally to the original geometry, you need to create these interfaces. This is, for example, of for the radial pump, I guess. So this rotor outlet and volute inlet connection has to be perfect, has to match perfectly, because then the accuracy is the highest. There are the methods that you can connect, for example, from one side the extended inlet, or extended in the axis direction, but from the rotor, for example, you have still the narrower patch strip. But the best accuracy you will have if the mesh has nice edges and the face alignment is perfectly aligned, and then this is the highest accuracy for interpolating the values from one part to another part. So another option, for example, just the example, that you can also apply the segment geometries for rotating symmetry geometries, typical for axial fan, but can be also applied axial machines, but it can be also applied to the radial one or centrifugal one. So in this case, the interface alignment is virtual, so you can have any relative positioning of the rotor stator segment, but the virtual full wheel interface has to align perfectly. The last one is the triangulation. So if you generating the mesh with, for example, SnappyX mesh or many other meshing tools, requires the STL format, and the STL format is the first triangulation or first discretization by the triangulation of the surface. And the finest of the triangulation also define the shape for the meshing part. So what I would like to say that if your triangulation is too rough or some irregular or whatever, and include some weird shape of faces or triangles, then this also affects your CFD simulation. As an example, for example, here we have the example of rough STL triangulation on the blades, and here is the pressure distribution for the CFD results, and this is the result of the finer triangulation. So as you can see, the difference is obvious, and this can give you another torque, different torque, because your original shape of the STL doesn't follow the original smooth shape of your geometry, on which, for example, from which you then create the model and or compare with the benchmark or whatever. So this is also important for the accuracy. The same holds for the interface connections, because again on the interfaces the interpolation or mapping has to be done, and if the original shape is too zigzag or has large triangles or is too coarse, both from the point of view of STL and also then for the meshing point of view, then the accuracy also decreases rapidly with the rough refinement or rough triangulation. So this can also affect the fineness and the accuracy. And last but not least, that for the meshing of the closed domain, you need to have the closed geometry. And again, from the STL point of view, because this is the first triangulation, the best you can have and you should try to export is the watertight geometry, which means every vertex of the triangle is connected to the neighboring vertex of the neighboring triangle. The same holds, of course, with the edges. So sometimes when you export different with some approach which don't see the connection of the neighboring surfaces, for example, it may happen that some gaps will occur, typically on the connection of the curved edges, and this can gives you bad meshing parameters or bad meshing quality, or sometimes the mesh can leak out from the geometries from the geometry, and basically the meshing procedure fails. Yeah, so keep in mind that also this point-to-point correspondence is best to have. If it's not possible, then you can heal it, or you can resolve it by fine triangulation, because fine triangulation gives you smaller gaps in this kind of topology of the STL triangulation. All right, so I think this was from my side of a detailed description of the crucial parts of the geometry shape and geometry requirements, and maybe a lot of them we will touch during our hands-on sessions. Respectively when I will show you the cleaning. So we will touch all these parameters and all these requirements. So I will be commenting it later during my cleaning part.
Yes,
So
yes,
maybe
absolutely. Yep.
perfect. Yeah. So
Yes.
let's go back to the Luboš and let's continue with other
Yes,
topics.
yeah, absolutely. Yeah, yeah, Radek. So let's do it. Can you now see my screen, or is it
Okay, not yet.
okay? I need to say share. Okay, I got it. Got
Mhm.
it. So I hope you can see
Yes, now
the
it's there.
presentation now.
Mhm.
Okay. So I'll continue. So this was the goals, principles, and some terms explanation. So I hope it's clear what we are looking for. We are looking for a geometry which is clean enough, simple enough, and relevant, right? That's especially important. The geometry has to be relevant to our case. So all the relevant, I would say, surfaces has to be presented. They have to be smooth enough to represent the to mimic the real geometry as closely as possible. So we have a couple of cases we wanted to show you because, of course, it differs where your data comes from, right? So sometimes it's automatically generated data, sometimes it's like low-level geometry, like STL files directly, and you need to play with them. Sometimes it's CAD, the CAD file, which needs typically needs to be cleaned and prepared for the simulation. So we have a couple of examples of each of these groups, I would say. So let me jump right into the case number one, where we wanted to show you what's the good representation of the goal, which is somehow an ideal geometry. Radek showed already quite a good one, the Kaplan turbine, which is the tutorial for TCAE. So I will just briefly go ahead with such centrifugal fan geometry. And Radek, by the way, I will be happy if you correct me if I say something wrong or no, or incomplete or something. And we have such an example, which is pretty standard geometry of centrifugal fan. And this is I would say someone did his job well in this case, because the case is split into components, and so I will just quickly show you what Radek just showed you before, but on other case. So this is the geometry is being prepared in a way what we call it the component thinking, because sometimes some geometry parts can rotate or can have different boundary conditions and can have even different physics. So it's smart to split every case into components, as it's logical when in its real physical representation. So typical centrifugal fan can have something like the inlet tube. We call it sometimes we call it suction. Then it can have the part which is rotating. So definitely it deserves its own component. Sometimes, for centrifugal fans we call them impellers. So impeller part, and then the spiral with a volute which is also necessary to make the pressure get more static, etc. Anyway, so this is an example what I wanted to show you, that a good example is to have three components which are following each other. So the flow comes into the machine through the section, and each such component has, yes, again, as Radek mentioned, it typically has its inlet, then it has typically the outlet, and then it has a wall, right? And all the components should have some corresponding order. So for example, the impeller has, again, it has some, let me see, the inlet, then it has the outlet, and then it can be split into, for example, to the shroud and the hub. And sometimes it's smart to split the blades into the trailing edge, suction side, pressure side, and the leading edge, because sometimes it's smart to have more surfaces. It's not necessary. So
yeah,
it's
that's important to say that it's not necessary, right? But
yeah.
it will improve and will give you more options to play with the mesh refinement locally, etc. But it's not compulsory, right?
Yes.
Yeah.
Yes. So we like it that way, but it's absolutely okay if you don't do that, and you will still your ambitions to good results are still high enough. So and so a good a good um, example is clean surfaces and to keep the relevant surfaces, because in fluid dynamics surfaces matter. Surfaces matter because fluid flows and all the integrals and all the important things matter, and happen all the important things happen on the surfaces, either on the walls or on the interfaces. So it's all about surfaces. And yeah, the simulation ready geometry is good set of surfaces that fit each other, I would say. Okay, and time is running quite quickly, so I'll go ahead a little bit. I have another example where we will discuss just a little bit how we can proceed when we have the STL files, because STL files we can have them from scan, or someone send them to us, and we don't have the access to, for many reasons. It may happen that we don't have access to the basic parametric geometry, but we only have the reduced geometry. But basically, those are the points and sometimes normals and triangles. So I have a little example, which is in Blender. By the way, I love Blender. I think it's really great software. It's open source. It's free to anyone. It can do a lot of geometry operations, but it's especially good on this low-level geometry. Here I mean, okay, let's call them STL files. I'll be speaking about STL files. So this is exactly the case, because we received from one of our clients this quite realistic model of Formula One, and Blender is really good on working with STL files. And for many reasons, it's usually good to have the model split into different files, because when you have different, I would say components, but yes, files, and in the external geometry especially, because it allows you to play with them, right? For example, you can replace the wheels, you can play with the wings, and uh, you can really play with them. So to having the model split into components is generally very good idea, because you can play with them, you can replace them and study their effects, right? So it's a good idea. And also the watertight property is very useful and almost necessary. It may happen that it's not possible to do that. Sometimes it happens, but usually you need to have watertight components of all the parts of your model. So let me explain or show you a little example. So I will pick something here. So I will pick this little guy. It's I don't know what it is. I think it's some kind of sensor. So let me take a look at it. So it's yeah, such a guy, which is, let me see. I'll jump into the edit mode, and it looks to me like it's watertight. It's closed. Let me do a little check here. If you download the extension, free extension to Blender, which is called 3D Print, which is a good tool for 3D printing, we can use it also here. And if I check my component, it tells me there are no non-manifold edges. There is nothing bad. It's really perfectly closed, and it's a perfect guy. It's a perfect component. I like it. So to be able to show you something, I'm sorry I need to cripple it in a way. So I will pick this, and look, someone just removed one face. right? So now it's definitely not watertight, right? There's a hole in it. There's a hole in a big hole in this component, and this could be an example of a bad geometry, right? So I have look, I have formula here, and this component, this guy here, is not watertight, and this could be a potential source of problems, right? Because if I'll click this this skeleton of the monopost, and potentially it's very highly likely if I make very fine mesh, what happens, the flow flows also inside this guy, which I don't want, of course, because it's I want to keep everything what should be closed has to be closed. Otherwise, there would be at least additional mesh cells. I don't want them there, and also these buffers and everything. So I want to keep everything closed. That's closed. It's very important. So to keep it watertight, keep it waterproof. Okay, so this brings me back to the guy. So it's not watertight, right? It has this hole, and Blender, why I'm here, I want to close the holes. Sometimes it's simple, sometimes it's easy, sometimes it's difficult, sometimes it's something in the middle. But okay, I have picked this guy, and what can I do? I can go to edit mode, so I can see the vertices, I can see the edges, I can see the faces. What's important? There are of course multiple ways. What I can do. But by the way, if I check again in the 3D print mode, if I check again, it tells me, oh, something is wrong. I have found, or 3D print function has found 16 non-manifold edges, and I can ask it to show me. So show me where the ugly non-manifold edges are, and it says, okay, Lubos, it's here. Those are let me see. Okay, these are the edges. These are the edges, and you should do something with them, right? So I can say okay. So I'm going to. It's possible to manually pick the points and then seal them with F function, right? You can play with them. Of course, this would be a little bit silly. Sometimes you want to do some engineering because the face may not be that I would say simple. So there are a couple of ways how to do. So I can use this X-ray, for example, and pick them, and then press F, which is it creates the face out of the resources I have given. Or of course, I think you got it. If I deselect everything and again ask the function to show me the non-manifold edges, I can ask it to make the manifold for me, or I can create I can seal them up with F shortcut, which is create the face out of the resource we have selected. Yeah, and if I escape it, I have it again repaired. So now this guy, now this guy is sitting on the top of the Formula One, and we can be sure that it's perfectly watertight and there will be no problems with it. And yes, sometimes when you have this low level geometry, you have to go component by component and seal them up. If you are in some research project, of course, if you're in some recurring project which is being repeated all the time, then you would need to find another solution, and there are there are solutions for everything, of course. But yeah, in research projects you can seal everything in this way, and Blender is really good tool for that. There are many possible visualizations and also point transformations, and the games you can play. There are really a lot of them. So the point from here is Blender is good, and if you can split the model to as many closed watertight components as possible. So I will go back to my presentation. I consider this, well, it's gonna be it. And let's go ahead a little bit. By the way, another just technical check. Radek, can you hear me? Is it still?
Yes, I can.
Okay,
I
okay.
can follow
Thank you.
everything, so
Thank you, thank you, thank you. Because
everything's
I
fine.
always like these kinds of confirmations that I'm not
Yes,
talking to
yes.
the wall, but someone hopefully is hearing. Okay, that's great. That's great. Let's go ahead. So I have another example because many times in especially in repeating workflows I mean in workflows where the repeatedly again and again and again and again, and there are big optimization loops, you simulate the same things, you should have some kind of automation, or in other words, for CFD preprocessing you may have some parametric geometry builder which creates the geometry for you, and it's already simulation ready, right? So it's another approach, and that could be this CF Turbo. We have a very good partnership with our partner from Germany, CF Turbo, which is turbo machinery conceptual design tool. And let me see if I can show something in it. We have just recently created a new interface with CF Turbo, so it's completely automated. So let me show you how it works. So, well, pretty anything what you export from CF Turbo, it can be automatically run in TCAE, but let's take a look. I'm picking this centrifugal pump. By the way, we love looking at rotating machinery in meridian view, but yeah, what's even more transparent is looking at the machines in the 3D 3D view. So let me check how the buttons are clicked, because it's always different in every software. Okay, right button on mouse is moving the object, left button is rotating around. I specifically like this function, it rotates for me, and the impeller is rotating now. Yeah, so now I'm in CF Turbo, and CF Turbo is very, very efficient turbo machinery conceptual design software. So you can design all the rotating machinery machines here. It's very user-friendly and very, very efficient. And we have very fruitful collaboration with CF Turbo. And I will just quickly show you, okay, this is such a case, normal case, a normal pump. It's their standard pump. Yeah. So I'm not gonna play. I'm expert on CF Turbo. I am not. So I will just go to the export. I will find the best software of them all, which is TCAE. And for TCAE, I will export, yeah, this model. It has three components. Also, CF Turbo has this component thinking because it's very logical and very straightforward. And I can say I'm going to export the geometry. It's because I did it just a while ago. It asked me if I'm going to overwrite it. I'm just going to overwrite it, and so now it's exporting, and it's being written down on the hard drive, and I guess it takes a couple of seconds. And I just did the automation. There are, of course, there are quite a lot of I would say export settings regarding the granularity of STLs, or you can export the periodic segment, etc., etc. But anyway, it's finished, and now, yeah, I did export it here, and I think I can directly open this. Hopefully, I can directly open this configuration file, and it's going to open directly in TCAE, and everything is ready for the geometry. So the point is, if you have CF Turbo, the best way whatsoever is using CF Turbo, or you can create your own geometry builder. It's not really difficult as it may look like. So we have seen really great customers geometry builders created in slightly in Python or in Salome, Shaper, or in Rhino. So, and there are many other tools which also in other tools. So there are really good ways how to create the geometry automatically. So this is the case. Yes, I can. If I click the automatic run, everything would run right away. I did it just a minute ago, and I simulated everything. And also the first thing I always look at is the efficiency, because efficiency it has everything in it, right? So if I see, okay, this pump has efficiency 87%, it already tells me that something has been done correctly, because efficiency it involves all the important quantities like torque and the pressure. So that means the simulation is likely okay. So CF Turbo is a good choice, or any other automated geometry builder is perfect for the simulation ready geometry, because it automatically does the job for you, basically. Yeah, so that's this. And yeah, time is running very quickly. It's 2 p.m. already, so 3 p.m. Sorry. So yeah. Let's go ahead. So we have the last case, the biggest case we wanted to show you. So it's the most common project scenario, which is, okay, someone has given me a cat model, which is it's a large dirty geometry, which is full of unimportant, irrelevant details. We have to somehow make it simulation ready. So the golden part of the webinar starts right now. Radek.
Okay, thank you, Luboš. I would not say it's the golden part, but it's the more work demanding part. Yeah, because the cleaning is the process of several basic steps to be done. So I suggest having a nice podcast you prefer, put your earrings and listen to nice podcast and clicking and cleaning the geometry. So you can do two tasks within one workflow. Okay, so I hope you can see my screen. So you can.
Yes.
So
The
I
stage is
directly.
yours, Radek.
Okay, thank you, Luboš. So now we will be cleaning the geometry in a really rough way that we have the geometry of the vertical turbine. So maybe I will directly load it. So now what we also like to use is Salome, which is also open source software. You can download it on salomeplatform.org pages, install it, and directly use it. So I will go to the geometry module. So Salome consists of several modules. Typically what we use is the geometry module. Then for meshing, for STL generation, and for nice STL triangulation, we use this meshing module. And there is also the geometry shaper for generating parametric models, which can be also handy, and basically you can create nice parametric models with a parametrical way of thinking. Yeah, so the shaper can be used for creating parametric models. But now we will stick in the geometry module, and here now I will import the step file we got from virtual customer, and we'll start cleaning it. And we will follow all the principles we are talking about in the first part of the webinar. So let's go for it. So here, live example, and at the beginning, I have the geometry of vertical Kaplan turbine. So I will load it, and let's go for it. So of course, you can use your favorite CAD processing software you want. So definitely some other tools could be the Rhino or FreeCAD or whatever you are familiar with, and whatever will give you features and utilities or functions which will help you to clean the geometry. So Salome is, let's say, so we can call it conservative way. So you can exploding, splitting bar, connecting part, and based on these simple steps you can clean, create, and pre-process the geometry. So this is what we have. Yeah. So as you can see, we have all the details. So of the vertical Kaplan turbine, so you can just connect it to the piping and you can run it basically. So we need to clean it. So as you see, we would like to extract the wetted surface. We will get rid of this engine and shaft part and other compartment. So let's go for it. Maybe just to see how the impeller and stator looks like. So you can see here we have the propeller with the hub. Here we have the stator and part of the shaft. So we need to somehow explode it and clean, get rid of the unnecessary part, and maybe some parts will be modified to and simplified for better meshing. So let's go for it. So what I will be typically using is this explode option. So this explode will allows you to explode the geometry into the subshape types of several types. So typically we start for more complex shapes, because typically the CAD model also consists of each solid part. So definitely we can select those parts which are relevant for us. So here I will click on the select subshapes, and as you can see, for example, I can export just the engine, etc. So I will go for this, let's say, for the duct system, for the shroudings. So I will export these three parts first. So as you can see, so this is just the piping. Yeah, so basically the outlet part, shroud of the stator and rotor, and the inlet duct system or inlet pipe, this elbow. All right, so this is fine. Maybe what I suggest you, maybe I will not follow my typical steps just to speed up the process, but I suggest you to name each part, to simply refer to the part. So for example, what I mean, so here you can name it as stator shroud. The other part, for example, could be the outlet, and this will be the, I don't know, the inlet, or you can call it, yeah, the inlet, for example. All right, but we will also need the other parts. So let's go for another decomposition, another explode. So again, I will click on the solid. So I will hide these three parts which I have already exploded. And now what we have here, so okay, we have the hub, we have the rotor, we have the stator, and we have the shaft. Here's another item, bearings or whatever. So I will get rid of it, and I will just then simplify the shape to smooth connect to the stator, for example. Okay, so I will explode these parts, and together with my already exported parts, so I think we have everything what we need, and so we will be processing these parts. So again, just to fulfill what I have said, okay, we can name it to easily refer to these parts. So this could be named, for example, shaft. This will be the rotor, and this could be, for example, rotor hub. All right, so let's go, let's say, from inlet and to the outlet and start cleaning the system, the geometry. Okay, so let's start with this, with the inlet. So if I right click, I can click here, show only. So now what we need is to extract just the wetted surface. So on this part, I can again click on the explode feature, and here I can select now face, select subshapes, and I would like to extract just the faces from which the inner part is constructed. So I hope this one. Okay, so anytime I would like to just see what faces I have extracted, so I will hide the inlet component, and we can see, okay, perfect. This is okay, this is fine. So just to connect them together, I like to create these shells. So it will connect the faces. So I will name it like inlet and for example, wetted surface VWS. I will call it the wetted surface extraction from each part. All right, so this is the inlet, and similarly we will follow for the other parts. So another part is the shaft. So this is the shaft part, as you can see, which goes through the openings here and will be connected to the stator. So I would like to explode faces on the shaft. So let me, and what I really like that we don't see the edges here, because I don't need what is in the external part to have a nice geometry. So what I can do is I can cut the shaft by my inlet to create the contours and to be able to export just the faces. So we can do the partition, which is here. Partition function. Tool object is my inlet WS, the wet surface. I can click apply, and now I can see I have nice cutting, which is nicely connected to my inlet elbow. All right, and just to see how the stator is connected, so I will visualize the stator. So as you can see, so what I will do, I will export just these two faces, and here from this edge to this edge to close the gap, because I don't want to model the flow here, because there was some connection plate, or how it's called. So I will create nice ring-shaped face which will connect these two edges. So I will explode the shaft part in this way. So again, partition, face, and select subshapes. Click on these two faces. Now I can get rid of this, and perfect. So this I have. And now I can create a connection. So the best way to create it, for example, I can create a line connecting these two edges, and then I can run the operation generation and revolution. So I can create this strip by revolution of a line. So this I can do in the simple way. So what I can construct is, for example, to create a point. Oh, sorry. Yes, create a point on the edges. So I can create. So what I click here to create a point. Now I can create a point on the edges, on any edge. So I will first I will choose this edge. I can define the point by a coordinate. So for example, I would like to have the coordinate with the highest y axis. So y is now perpendicular to my view. So for example, I can click here to have some maximum y coordinate, and it will give me the maximum at the point on the edge with the maximum y coordinate. So apply, and the same I will do on this side. So by coordinate, apply, and now I have nice line with the same y coordinate. So it lies in the symmetry plane of these two, of the shaft and of the stator. So I can create line connection, and from this line I can create new entity, generation, revolution, and because my original the geometry was positioned with respect, or the axis of rotation follows the z axis, so I can rotate it along the z axis, and I need to create a full revolution. Click apply, and now I have nice face which connects me the shaft with the stator. So now I have these three faces, and again I can create a shell which I will call shaft minus ws, like that surface. Nice. So now I have these two parts, as you can see, and I can continue cleaning the other parts. So let's see how the stator looks like. So I will get off this inlet. I will keep just the stator and stator shroud I would like to see. Okay, so this is pretty nice aligned. And what we can see, I'm not sure if the stator blades are nicely cutted into the shroud. So this can also bring some troubles for the meshing. So if I click on these shroudings, click on the transparency. Okay, so as you can see, I don't know if it's see on your screens, but it seems that the blades are not cut into the shroud. So I will have no edges, for example, to export the nice contour of the shroud in which the surfaces of blades are cut in. So what we can do is that there is the operation, either operation that I can maybe, okay, first operation could be that I can cut off the part of this of the stator by the stator shroud. Maybe I will show you what I mean, but then this operation is more complicated. That, as you can see, yeah, there is not nice cutoff. So you can see that the stator blades are longer than the shroud radius, the inner radius, and this can bring me some troubles with the meshing, because during the meshing, the mesh snapping is done to the edges of to the boundaries of each patch, for example, and it can create me some zigzag shape that the snapping during the meshing will be snapped to this edge and not to this contour versus the stator blade contour, basically. So I can do it in this way, then I can explode it and cut off these parts. But there's a more clever operation, which is the fusion. So there is a Boolean operation and fuse, and I can fuse any two objects. So I can click on stator and stator shroud, and let me try it. Okay, Boolean driver failed, and typically, I don't know what is happening, but typically this operation remove extra edges fails to complete this operation. So if you uncheck it, and now if you see it, we have nice contour here, if you can see it. So this is exactly what we need. So we have fused these two parts. So now we can again explode the faces and get rid of the solids. So what I do, again, I will click explode. Now I will explode it to all faces, because it's not easy to pick which faces I want to keep. So I explode this fusion part, uh, explode all the faces, and now we can simply manually delete the upper part. So therefore I suggest you to run some nice music or a podcast, because some operations are really boring to make and needs a lot of clicking. So it doesn't require any thinking. So just select, delete the parts, and the other parts. Okay, I don't need the inner part of the stator. And okay, I can get rid of this and also of this, because if I show you the rotor part, this right away connected to the stator. All right, so get rid of these parts, and yeah, this is perfectly what we needed, I guess. Yes. Okay, so now we have again the wetted surface, the shaft is nicely connected, the rotor will be connected. Okay, so I can again create a shell from all these faces. Perfect. So I will call it just stator wetted surface. All right. So now we have also the stator cleaned. Now we need to, let's have a look on the rotor. So rotor is nice. So we just need to get rid of this volumetric part or this solid part, inner part, which we don't need. And let me just check the outlet. So I think it's also nicely connected. So I will just then explode it, and we will be finished with the basic cleaning. So let me just visualize. Where is show only? Yeah, here. Now I will explode it again. So I will explode all the parts. Okay, and now then I will just delete the inner faces to really have only the part we needed. Okay, that's nice. So again, I can put it back to the shell, and this will be the rotor wet surface. Okay, and finally we can do the outlet. So again, let me click here, the outlet part, and this will be pretty simple. So again, explode face, and now I will, okay, this part, and now I will select the subshapes, and these are just 2 or 4, yeah, 4 faces. Apply and close. Let me see it. Yeah, nice surfaces, and I will name it outlet WS. Okay. All right. So let me check all our parts. So I will collapse these big parts. So let me go one by one. So show only the outlet. Then we will have the rotor. We have the stator. We have the shaft somewhere right here, and the inlet. All right. And when we check it, okay, there is a big hole. So I forgot also to explode the hub part. So let's go back and rotor hub. Perfect. So what can we do? So this is how the rotor hub part looks like. So okay, I will focus just on this. So I need to extract these faces, creating the surface. I don't need all the solids inside surfaces, and then I need to close this gap. I think that the shaft is connected and somehow mounted to this part. So I will create a simple face. I will just close this circle shape. So what I can do, I can create a shape for edges. So I will explode the edges on this tip of the hub. So I will explode the edges, and if you select all the edges, okay, I will just focus on this part. So edges, and here there's creating simple shapes, so I can build a face from the edges. Apply, and I have a nice face which close me this tip gap. Now I will explode the faces from the rotor hub. Okay. Apply and close. And now I will put everything together, and I will create again the shell, and I name it rotor hub WS. Okay, show only. And we have nice hub. So we have the rotor hub, we have the rotor connected to the hub, we have a stator connected to the rotor. Okay, we have this outlet part, we have the shaft. Where is it? Here is the shaft, and the inlet tube. Perfect. And just to refer to all, because this is my cleaned wet surface from the original shape. So I will create a shell from all of them. Nice. So as you can see, this is our basic cleaning. We have extracted the wet surface, and we made some simple simplification of some complicated parts. So we have created a connection here, and we have closed the gap on the tip of the hub. All right, and now what we need to do is to create. So now we did the cleaning. Yeah, I also visualized this simplification, let's say. And now what we need to create this to follow the component thinking, we need to create interfaces. We need to create the interfaces and also the inlets and outlets. So let's start, for example, with the interfaces. So for ease of work, I will create just the one rotor, one stator, the inlet section, including the stator blades. Then we will have the rotor, and the rest will be the outlet. So I need to create two interfaces. So I can create by planes. I will show you. So I will cut it by planes and create nice interfaces. So you can create a plane by point. So now we have here, for example, the best way is to put the interface just between in the gap between the stator and rotor. Yes, so typically to have to both the same sizing from the both sides if the stator and rotor are close together, because if you put too close to the edges, then the mesh refinement should be really high, which brings a lot of cells. So we need to place it in a proper way. So the best way just in the middle, and I think this contour on the hub, I think, could be just somewhere in the middle between the trailing edge of the stator and leading edge of the rotor. So I can put point on this edge, which is here. Vector is Z. So I will create a plane, small plane. Okay, so this will be my cutting plane, and using this plane I will create the interfaces. And the same I will do on the other side. So here, what we can do, I will create a point using which I will define, what I did, using which, okay, I just modify the camera view. So let's go back. So now, for example, here I have the edge behind the stator, behind the rotor trailing edge. So I will create a point here, and because I have no, I'm somehow I have a space where to put the interface, so I can create a larger space behind the rotor, so I can move the point more further. So for example, 1 centimeter behind this contour. So I just click here, and then I just modify the Z coordinate. And then I will use this point to create a plane. So vector in the Z direction, I will make just smaller size of the plane. And now we have these two planes. So first, what I will do, so I would like to create the interfaces just in my flow path. So I will check these two planes, and I will cut them by my cleaned surface. Okay, so now I have these two faces, so I can explode them and extract just the faces, which creates me the interface. So I will extract this one and this one. Okay, so I have these two interfaces now. Here's my wet clean surface. So I have now these two interfaces, and what I would like to have also is to have the contour right here in my shroud section, because then I can just export this part as a shroud for the rotor, and the rest for the outlet piping, and the rest for the stator shroud, for example. So what I need to do is to cut also my cleaned shell, this clean part, by my planes. So I will do in the opposite. So this is my object, and tool objects will be these planes. Okay, apply, and as you can see now, I have these two contours which will define me the boundaries for exporting these parts separately for the rotor. All right, so this is it. Now I need to put everything together. So maybe first I will also create I need to close the inlet and the outlet. So I can do additional splitting or exploding. So I will create partition, edge, select subshape. Now I will choose these edges at the end. Okay, these two edges. I will click here, create a face, perfect. And the same I will do on the other side. So explode, edge, select subshape. Okay, and I will do it manually. So here I have 3 edges, I hope, and now from these 3 edges I can create a face. Perfect. And now I can what I have. So where is my okay, so here is my partition, just to see what is inside. So this is my partition. Now I need to also include the faces, the interfaces, and my inlet and my outlet. And this I will put into my whole object. So let me check if the shell will work. Okay, if not, because of some not perfect connection, I don't know why, so it will just create a compound of shell. So I have the object, I have a simple object under which I have all my wetted surfaces and interfaces and inlets and outlets. So this is basically, I'm done with the cleaning. I just need to make a transparency just to see that the interfaces are included. Now I have the inlet and I have also the outlets. So this will be this is the part of the cleaning. So let me save my project. I will go, okay, I was there, sorry. So my today's example, cleaning, I will call it the part with the extraction of wet surfaces. Okay, so this is what I needed. So first I have prepared the geometry, I extract only the necessary parts, I created the interfaces, and I closed the domain with to have the inlets and the outlets. And now I need to create the STLs, and also I need to extract the parts which I need for the boundaries or for meshing purposes. So basically now what I need to do is to create these kind of splittings, and because the splittings is already done, I need to just assign or name the parts of my geometry of my surface. So I can name it as all, like I have all there. And now what we need to do, and it's, let's say, other boring stuff, is to create groups on my surface. So I need to create groups based on the faces. And now you need to name each part separately to be able to extract it separately. So basically what you need to do now is to select parts and create a name. So I will name it, for example, this is stator inlet, and this face creates the stator inlet. Now I can create apply, and then what you will see is that here in the pipeline browser, now we have the group here, and then we can refer or export it or create a triangulation, whatever. So this is another task is to create the groups. So for example, you need to do it in this way. So what I like, I select some parts of the new group. I will click add, and then I will hide what I have chosen just to see which parts I need to add. So hide. Okay, so perfect. So this will be the elbow, and I will name it as stator wall. So this will be my stator wall. In the same way, we can continue. So, for example, now I will create a stator shroud, height, and also the strips, I think, belongs also to the stator shroud. Yes, so I will also add these face strips, add just the height, okay, and this will be my stator shroud. Yeah, and in the same way, you need to do the rest. So, for example, what I also like, if you here select all your groups which were already defined, you click here add, then to click into this list, then you hit Control A, like select all, then you can click hide, select it, and remove them. So now you can continue with splitting. So for example, now you can create a shaft, you can create a face pressure side, stator pressure side, etc., etc. So now I will jump in time. So I will save my project, and I will open the project where I already named all these groups. So I think here workflow, and one of my project is here groups. So I keep my fingers just to have everything what I need. Yes, so perfectly. So this is my shape. This is my shape. And okay, and what I haven't shown you yet that is that you can also create some additional extension. So for example, a new component which extends the inlet, and this will be also created as a new component just for the extension, which I haven't done in the live example. So, but you can create pretty simply. Maybe I will quickly show you how it can be done. So if you have the face, I have it maybe here somewhere. Okay, or I can show for the outlet. Yeah, so you can click on the face which we have created. You can create operation or sorry, new entity, generation, extrusion. Now you set the direction of the extrusion, which is Z, and reverse, of course. And here you just select the distance of the extrusion, and in this way you can create quickly extrusion. Then you will create a shell or compound of shells to have a single object, and then you will create the groups on them. Yeah, so in this way you can create nicely extrusion if required. All right, so now what we have is the groups definition. So what I have here, for example, I have created the stator shaft, yeah, stator hub, and splitting of stator blade leading edge, trailing edge, pressure side, suction side, stator shroud somewhere, inlet shroud. So maybe, yeah, it's bad naming, but this is the stator shroud, etc. So now one option is to extract the STLs directly from these parts, but what what you can face that because each part will be extracted separately, then the point-to-point correspondence will be corrupted. So let me show you the example. So okay, you can click the part, you can directly click here, file, export STL. Okay, and I will export it here. So okay, I will export it here. So stator hub, I will click save, And the same I will do, for example, for this interface, just to have the common edge, just to show you the if everything will be fine or not. So this part, okay, I need to go for file, export STL, save, and now I will go on my disk workflow, and here I have these two parts, so I will open them in ParaView just to visualize what type of discretization was directly exported. So this is the interface. So I will, where is it? Here I can choose surface with edges, and to this, okay, here I will choose 3D view to be able to adjust the view, and now I will add the stator hub. Again, surface with edges, and this is basically, yeah, what you can see. I think if we zoom, this is the, okay, I render view. I hope you can see the gap here, because it's not point-to-point correspondence. So basically, this is connected to the problematic I have shown you on this slide. Yeah. So this will not this will not force this exporting the parts separately will not ensure you the point-to-point correspondence of the connecting STLs. Of course, you can, if you're exporting it, you can increase the deflection, yes, which makes the STL export finer and the triangulation finer. So let's check it. So this was the interface. So I will hide him and I will open the new one. So now surface with edges. So I know it will be visible. So this was the original one, and this is the more refined. But still, the problem is much more. So also you need to refine more the stator, and all the parts should be refined to the same level and to the pretty fine level. So, but the second choice is to create or generate the surface triangulation using some advanced algorithm, which you can do here in this mesh component or this mesh module, and it is done pretty easily. So you will check on which shape you would like to create the surface triangulation. Here you will click on create mesh. We need to have the 2D mesh because we do not have solids, we have just the surfaces, and the best algorithm is this NetGen 1D 2D, and here you will define the triangulation. So what I can set some basic one. I don't know, let's try this one. So this means that the largest triangle will have 1 centimeter, and the smallest triangle will have a 5 millimeters. So I think it will be too coarse for the edges. So let's try 0.5 millimeter. So okay, apply and close, and now by this compute, or you can right click the predefined mesh, and here you can somewhere run compute. So now the triangulation is running. So it basically discretizes the surface based on your input geometries and following the triangulation parameters. So I hope I don't put so too many refined mesh. So maybe let me cancel it just to speed up the process, and maybe I will set it to more rough mesh. So again, I can click here just to modify. Okay, and I will put, for example, this one. So of course, this parameter also needs to follow all the details in your geometry. So if the edges of the rotor blades are, for example, of 1 millimeter size, so then you need to go lower for for the minimum refinement level to be able to properly discretize these curved areas and curved shapes, basically the shapes with a high curvature. All right, so this is it. So now, as you can see, we have a nice, pretty nice triangulation with point-to-point correspondence. Here, if you have the mesh and group on the faces, so you can, for example, we can visualize this stator hub. Okay, and I will get rid of the whole mesh. So this is our stator hub, and if I visualize also the interface between the stator and rotor, so now we can see perfect triangulation and perfect matching. So the same holds, for example, for the edges. So if you visualize the edges, so for example, you have pretty coarse edge refinement, so this should be smooth. So what you can also do is to create some submesh refinement. So you have a general refinement parameters, and then you can apply additional refinement parameters for the algorithm on the separate parts. So you can create a submesh. I can create them on the stator, for example, stator blade leading edge. And here I will put new refinement. And for example, here I will put half a centimeter. Oh, sorry, half a millimeter. Okay, apply, and just quickly, okay, maybe what is also good is to name the submesh with the same name like the geometry input. And now I can click compute submesh. Let's see what will happen. Okay, and now you can see that, yeah, it's much refined and much smoother. And the same way you can apply on any part of the geometry. So this brings me to the last. So I will open the surface meshing. Okay. So in this example, I set all the meshing parameters everywhere to have a nice and smooth meshings. So for example, when I show you the stator hub and the edges, so you can see we have nice smooth triangulation, and now we can simply export each part separately, which is another boring stuff here in Salome. Unfortunately, there is no one button export for all the parts. So basically, what you need to do is to put export on any part, and basically export each part separately in this way. And if you do it, at the end you will have the list of all the STLs which are ready to be used for setting the T-mesh and applying for CFD application in TCAE or in any other tool. Okay, so let me show you how it looks. So we have now all the STLs needed for both defining the components and defining the boundaries. So if I group them just to have a different coloring, just to see how the mesh is split. And okay, for example, this coloring will be better, for example. And what I can do, I will create okay, for example, clip just to see inside. So this is our splitting. So here we have the inlet duct component, so inlet with inlet piping extension. Then we have the stator part where the boundaries are the interfaces and of course the wet surface. We have the rotor part, and we have the outlet part. And because the shaft is a separate part, we can set it as rotating. The stator we can set as not rotating, and the same for the rotor part. Everything will be rotating except the shroud. And because, for example, we have separated this blade cap part separately, so then we can put high level of refinement to really to nicely match this gap between the shroud and the blade cap. So in this way, this is basically what you need to do for cleaning your geometry. So as you can see, the input geometry was not so easy and so clean, and we were be able, okay, some steps I speed it up, but anyway, within 1-2 hours, you are able to process your shape, export the STLs, and have everything ready for the CFD workflow. All right, so I think from my part and the Salome application and the cleaning point of view, I have shown you what I wanted. So I think we can go back to Lubos to conclude, and maybe Lubos will have additional note to my workflow. So
yes, thank you, Radek. Thank you very much. It was perfect. I liked it very much. I enjoyed it. I followed closely. And
perfect.
yes. I think we can keep you as a presenter, and
Okay.
because soon we will move to Q&A. So I would
Mm-hmm.
ask now the audience to ask your questions. We will do our best to answer them. All of them will be answered. So take this opportunity to ask the questions. We'll do our best to answer. Uh, Before we go to Q&A, I have a couple of questions. Sorry, a couple of notes to this. Yeah, this is what Radek have shown. Is, I would say, it's Champions League, right? It's the perhaps the best what you can do, what you can do with it. So it may have looked a little bit complicated, right, and complex. Where in fact it's not. You will very quickly improve when you do this, and not every time you have to do this, right? This is like more like a project work with the, I would say, with the highest ambitions to fit the measurements, really do the benchmarks. So this is, yeah, this was the Champions League. So everything can be either done simpler, faster, to neglect some details, so to make it easier to some level. And so this may have looked difficult, but it's not the difficult. Everyone can learn it. I sometimes make a parallel to riding a bike or driving a car, right? No one is the best
Right.
driver the first day. No one is the best bike rider the very first day, but after some time it gets so much easier after some practice and learning some skills and knowledge. Yeah, so this was the cleaning of the step file of the dirty geometry, which is simulation ready, and I would say such geometry has the highest options to meet the best possible results. And by the way, for hydro turbines, we can get nearly perfect results with this uh, geometry. Okay, so it was this. There are another scenarios, right? You can have some geometry builder which is preset. Almost everything can be automated. Almost everything can be made easier. But this is what could be your highest ambition to do this. Okay, so let's move to the Q&A. So let's keep Radek presenter still, and I'm going to open the questions if I see one. Let's answer them. So Stefan is asking whether the recording will be available. It's a typical question. Yes. The recording will be available, and you will be notified via email that the recording exists. So you can see it, and you can I think at least the Radek's last case can be created from scratch. Also, the cases are available. It's not proprietary geometry. It's open, so we can give you the cases and also the project and everything. And also we will continue with this geometry in next webinars, where we will create the mesh for it. We will create the simulation setup, and we will do the post-processing of this geometry and similar geometries. So all the geometries we show in our webinars are freely available. So just send us an email. We will share it with you. Okay, Vanessa. Hi, Vanessa is asking, can I set default settings for the meshing and load point, and so on in CF Turbo. So I don't have to change it every time. Yes, you can do that. Well, yeah, for the simulation, you have most of the settings right away in CF Turbo. You do it there. You say what's the flow rate, what's what, and this single point is loaded directly in TCAE. And yes, this single point can be simulated right away, absolutely automatically. You do not need to set anything. Maybe number of processors, because typically the default number of processors is, I think, 6, but that's detail. The rest is perfect. And yes, the when automated, and you can set the other simulation points. You can add more like higher flow rates, lower flow rates to receive complete characteristics. So it's pretty much ready for that. Yes,
Yeah.
automated with CF Turbo.
Yeah, and if I can add that,
Absolutely.
you can
Yeah.
also, if you have a template, for example, from the point of view of the TCAE, and you have your best setup, so then you can just replace the input geometry, and the rest remains the same. Yeah, so you can have your template set up for the TCAE, where you have the best results, for example, and then you can just regenerate and re-export new shape of your geometry and run the whole workflow with the new set of geometry, and you don't need to reset or modify any TCAE parameter again.
Yes.
So
Everything
yeah,
can
I
be
think
highly automated. You can just uh, you can just modify XML files and just rerun CF Turbo and together with TCAE anytime. Just change the parameters and receive new results, and you can run it in the loop. And there are endless options how to do that. So yeah, it's highly yeah
yeah.
synergy
Yeah,
in these
and
terms.
there is also a simple connection to the T-opt, right? So the T-opt can manage these loops. So this is
Yes.
also the part of the automatization.
Yes, I'm looking where the questions are. Yeah, also another question from Vanessa, which is the original one. Is the component map created automatically? Yes, the component map is which is part of any TCAE setup. And yes, when the geometry is created in CF Turbo, then the geometry the geometry is well, yeah, sorry, it's in Tmesh.
Yeah.
Then the geometry is inherited from CF Turbo, and also the component map is inherited. So there's typically some suction part, some rotating part, and some spiral or volume
Yeah.
part.
Maybe
Yet yes,
you can
yep.
also show it on the CF Turbo example if you have still open it, but I'm not sure. Yeah, here
I could
again.
show, but I would only embarrass myself because I can't
Okay,
work
okay,
in CF Turbo. But
okay, okay,
yes,
okay.
I guess you can.
No,
Uh,
I mean in TCAE, but exactly for this export. Yeah, for this.
Sure, it's here.
This is
It's
what I
here.
meant. Yeah.
It's this one. It's this one. It's
Yes,
this
yes. So if you go
centrifugal
to the
pump.
T-mesh, then there will be the component map automatically created. Yes,
Yes, Radek. Thank you. Sure.
yes.
Yeah,
Because
absolutely.
yeah,
I'm.
when you export it and load it into TCA, it is ready for the computation, right? So this is some default parameters are set, and it is ready to run. So it will give you first impression of the results, and then you can of course play with the setup to achieve more accurate or
Yeah.
with different flow
Yeah.
rates,
Yeah. Yeah.
etc.
Yeah. But the principle is the same. It's the if you have the options, and if you can create the workflow yourself, just put it in the components. And in the component graph, you can see the flow, how it goes through the first component to the second one, to the third one, to the last one, and via which interfaces, and you can see it in the map. And of course, the map can be so much more complex than it looks like,
Mhm.
right? If you, for
Yeah, yeah, yeah.
example, maybe a quick example. Yes, I have it here, right here. Uh, there could be workflows with much more complex topology, and even so much more complex topology. This is just a simple external something, and the topology can be with more interfaces. Uh, But the point is there's a lot of flexibility involved. Okay, so let's go ahead with the questions because we are pretty long here. Yeah. Questions. So Radek, if you see some question, please go for it, and I will do the same.
All right.
Okay,
Okay,
Konstantin.
there is a question
Cancel.
from Matthias. Hello, Matthias. Does the skewness of triangles in STL affect the mesh quality, skewness or edge refinement in SnappyX mesh? Well, it uses the triangles just to define the surface boundaries. So if the skewness itself affects the shape of the edges and the shape of the surface itself, then it can affect the mesh quality. But in general, it should only if it's followed with some additional flow or the error. So in the first way, the first point, the snapping is done to the edges. So if the generated edges are okay, then it's okay. And if the shape of the surface is still good, even for the skewness of triangles, then I think the impact of the mesh quality is pretty low.
Yeah, I think so, Radek. I think the skewness and the bad shape of triangles, unless they're completely distorted,
Yeah.
right?
Yes, because it just defines the shape. It doesn't
Yeah,
use any property of the triangles itself.
Yeah. But in general, we recommend, but Radek said it, I guess. The basic triangles should be finer than the mesh, right? Otherwise it would not make a sense. So the basic input geometry triangles should be finer than the resulting mesh or expected mesh or requested mesh, if you know what I mean.
Yes. Another question I see from Zachary.
Okay.
Do you have any preference between Blender and Salome to pre-process the geometries? So, for example, I'm more expert in Salome and Lubos is more expert in Blender. And for example, in Salome, you can't process the STLs. So Salome can handle the step files, IGES files, etc., but fine STLs cannot handle because it treats every triangle as a new face, and it's almost impossible to directly import STLs and play with the STLs. So to process the STLs and heal them or modify them, it's definitely better Blender. And for example, from my experience, but I almost 99% of preparation I do in Salome. So but Blender has many features, but also for rendering, right, and visualization, etc. So
yeah. I would only mention that if you have like high-level geometry step files, then Salome is definitely better. If you have low-level geometry, like some scans or some 3D data like STLs and nothing else, just only STLs, then Blender could be better because it's so much more ready to operate these low-level geometries. So it depends. There are also other tools, right? Like FreeCAD. We don't use that much FreeCAD, but we have heard it's not that bad. There's also Open Cascade, right? Which is also possible to use. And we know that, for example, Rhinoceros is it's not open source, but it's really I would say affordable, and it's definitely really great software which can be highly automated. Geometries can be parameterized with Grasshopper, and also it's very usable for these simulation loops, parametric loops, and parametric optimization workflows with TCAE. So there are a lot of options, and pretty much it depends what's your basic source data, what are your ideas, what are your strategy, and if you don't know, we'll definitely be ready to help you or give you advice. Okay, questions.
Okay, I have another interesting one, so
please,
maybe I can mention it. It's a question by Wolfgang, and the question is: when meshing interface surfaces with the same level of refinement in Snappy, will the mesh be identical on both sides? The answer is no, because the meshing are done separately, so it's not connected to the neighboring components. So it's like two separate meshes then connected together. And in general, if the background mesh topology and sizing is the same for meshing both sides, then the mesh will be, and with the same level of refinement and the same level of refinement of the connected surfaces and the parts in the neighborhood of the interface, then likely it will be really similar, but not the same like applying for cyclic boundary condition or whatever. But in general, they are not identical because
mhm.
it is meshed separately. So this is a good question, but it's connected by the AMI, and if the interface curvature is, for example, flat, like for these interfaces, then the mapping is very accurate. If you have these interfaces on for example, this circle or cylindrical shape, like for centrifugal uh, pumps or fans or whatever, so then a higher level of refinement will give you more accurate interpolation, of course.
Okay. Yeah.
It's a good question. Yeah.
Him is asking how compatible are SolidWorks for surface models to be used in CFD? Uh, uh, to be honest, we do not know much of SolidWorks, but we know our clients use it, and I would say it would be very similar. The principles will be very similar to Salome, and it must be achievable. The same workflow has to be achievable in SolidWorks as it is in Salome. I do not know about the surface meshing features in SolidWorks, but I guess that there must be something for it. So very similar. The principles are universal, and the tools to be used are yeah, optional, always optional. And yeah.
Yeah.
Yeah,
There was some
yeah,
question
please.
connecting to the refinement of the interfaces. So this was just the generating the interface from this STL point of view. Yeah, so it does not affect the 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 mesh which is generated on the interface. It just defines the shape of the interface for the meshing. So the mesh is not, it was not done in here. It We just generated the STLs.
Yeah. Yeah. The mesh will be the object of some other
Yes, or the
webinar. Or
perfect.
actually
Just to be
the
clear,
next
yeah.
webinar will be, yeah, about it. Okay, let's go ahead. Mathieu is asking, what software should I use to simulate liquid rocket motor, turbo pump, and combustion chamber? Uh, uh, yeah, again, it's not ripped in stone what should be used. It depends what are your basic data, where you start from, right? If it's some cat data, you should use something like cat. If you have some, yeah, low level data, then it's always question. This is difficult to answer, but if you also there's also a question if you have some budget for it, or if you strictly want to need to go for open source. Salome is always here, Blender is always here. Depends. Yeah, the same answer. We have shown just the principles that are universal, and it's up to you how to use it, and uh, depends on the details of every project. Okay. Okay, I think Radek, it's time to conclude.
Yeah, yeah, we are more than
There are
2 hour
several,
long, yeah. So we
yeah.
will answer all the other questions later, right?
There are other questions, but we have just made this Q&A. Thank you everyone for it. If you have other questions, when you see the recording or whatever, just feel free to contact us. It's universal advice and suggestion. Just contact us anytime, and we will come back, and we always talk to everyone. Yeah, so this would be it. And I would like to thank you all for your attention, who made it our heroes, because we were like, oh, well, more than 2 hours long.
Yeah,
So
yeah.
thank you everyone for your attention. Feel free to come back anytime, just for a question or just say hello, and let's see what we can do together. And we will leave you with that. And bye bye for now.
Thank you and bye-bye. Have a nice day.
Bye bye. Thank you. Bye bye. Yes. Whoa, 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 whoa. Yeah. What is going on here? I think the broadcast has just started, right? So since this very moment, Radek, people can see us and hear us. I hope for it, actually, but we have to be very careful what we say from now because we are too lazy to cut the webinar, right?
Yeah.
Since ever, but we do not cut it anymore. So this will be part of the recording already. Yes. So the last check, Radek, is everything working? Do you think it's
Yes,
working?
I hope so. I can see you. I can hear you. So I think
I
from your side, everything is working. I'm
Okay,
not sure
okay.
if you can hear me.
I can hear you. I can see you.
Great,
Yes,
great.
yes, yes. And yes, Radek is sitting in our bigger meeting room, right?
hmm
In our CFD support
With a
office in
nice,
Prague.
yeah.
Yes, CFD support. Yes, so bigger meeting room, and I am in exile, right? In exile in the smaller meeting room, right? Which is
Yeah.
not as nice as
Yes.
Radek's room, right?
Please
Right? Not
don't
at,
move your
at all,
camera, right?
not at all. But
Yeah,
yes,
don't move your camera.
I won't. Yes, good point, Radek, good point. It has to be set exactly this way, and people should see only this, what you can see, which is, by the way, quite, in my opinion, Radek, it's quite like sterile environment, right?
Yeah.
It's like white nothing. I'm sitting
Yeah,
in
we
the
should
middle of
equip it by
nowhere
some
in the small
nice
meeting
pictures.
room
Okay.
with nothing, right? And you know what? I'm still quite happy because we are having webinar today and we are engineers and our happiness and our I would say entertainment is not on the walls, right? It's in the
Yes,
computer, right? And it's simulations.
exactly.
It's
Yes.
accurate results and converging simulations and happy clients and happy friends and happy everyone. So it's one long parade
Perfect.
we are having here for 15 years already. Yes.
Oh yeah.
And by the way, on my clock it's 2 p.m. So let's get to the action. Right. So Radek, the webinar has to start, but
Yeah.
I
It's
need to
being
share my
recorded.
screen.
Yeah,
I
it's
need
being.
to
I think it's
it's being
recording. Yeah.
recorded. Okay,
Yeah.
and I'm going to share my screen, which is this. I was
hmm
just playing a little bit with my presentation. I will home it, and I think it's time to start the webinar, right, Radek?
Yeah. It's already
Okay,
started.
okay, it already started, yeah, so people can see this and yeah. So okay, so I will wait 5 seconds in completely in silence, and then I will start. Hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we will show you how to create perfect CFD simulation setup, right? So as you can remember, the last webinar was about CFD preprocessing. It was about how to prepare simulation ready geometry for simulation setup. And today's webinar is dedicated to simulation setup. So we are looking forward to it. So what else? The webinar is being recorded and its recording will be later made publicly available on our YouTube channel. So yes, there will be a recording, a typical question from our users and attendees. So there will be a Q&A session at the end where you can ask your questions. So feel free to ask your questions. This webinar is quite content-like webinar, so you can see a lot of important information for engineers. It's not one big ad on our products, but it's really I promise you can really learn things in the webinar, and we will be happy to share it with you. Okay, so we have this setup. Together with me online, I hope still is my colleague Radek Maca. Hello, Radek.
Hello, Luboš, and hello to the audience. And I wish you a good day and great webinar today.
Yes. Radek, it's a pleasure to have you here because you're the real expert here. I'm only responsible for communication with our users and with our partners. So thank you for being here with us, and I think we can start and let's see what we can do.
But and don't be so humble, you are also expert in CFD, definitely.
Okay, thank you very much. Okay, no, yeah. So let's do that. Let's do that.
Yep.
I'm doing it, and also Radek, I think this is the very time we will switch off the cameras
Yep.
and provide our users even better aspect ratio of the on the display. So
Definitely.
we are still here, but our images are going away for a while. So I'm switching off the camera. So yes. So I hope our users can see pretty much my screen at the moment.
Yes,
Okay,
I
so
can
the
agree.
webinar is really here. This is the agenda. So in the 5 minutes, but yes, only in 5 minutes, I will mention all the necessary information about what's on the table. If I'll be longer than 5 minutes, I will buy you a beer when we will meet personally next time. If I'll be longer than 5 minutes, so I'll be very careful to be shorter than 5 minutes. Then we will start with general thoughts about what we think about how the simulations should be done, could be done. And we'll start with general thoughts, and we will be going to more and more particular details in the webinar. So we will start with general thoughts, what we think of about how to set up simulations, what are the smart tips and tricks, and special how-tos, what we think it should be done, and then we will go more to like goals, principles, and thinking of engineering simulations. And then we have two cases. In the first case, again, it will be rather quite general, very simple pipe flow. I'll show very quickly some principles about how to set up the case. But yeah, very simple. And in the larger case, Radek will show quite a more detailed example how to set up, specifically how to create the mesh, because it's always very important to create the mesh, and how to set up the critical settings of Kaplan turbine. And then there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. We will answer all your questions. The most relevant and representative questions will be answered right away in the webinar, and the rest will be also answered, but via email when tomorrow, I guess. Yes, and there will be then the conclusion, of course. So I will start with when one idea which just popped up in my mind. We will be showing things in our simulation environment called TCAE, but we will show general principles. So you can be sure that if you have another CFD software or standard CFD software, you can find the similar settings, similar principles. There's only one nature and one universe, and typically the simulations are done similar way. So yes, we will show everything in TCAE, but the principles are universal and pretty much useful, I guess, in other software, especially in open source, open form, etc., etc. Okay, so I will start, and I'm starting now those promised 5 minutes on my timer. Yes, so the next webinar will be dedicated to CFD post-processing. So today we will not speak too much about CFD post-processing. Today it's about CFD simulation setup. So once again, I just repeat, this CFD simulation series is about, the last webinar was about pre-processing. Today's webinar is about simulation setup, and the next webinar on June 17th will be about CFD post-processing. So today it's about the mesh and simulation setup. Okay, so looking forward to it. Just quickly, CFD Support is the company name. We are located in Prague, Czech Republic, 15 years in the market, hundreds of professional projects, consultancy projects for the industrial users of industrial applications, and much more to come. We deal with CFD, FEA, FSI optimization and acoustics. So we primarily deal with engineering simulations. We are quite compact, small team of well-educated engineers who take the things very seriously. We provide consultancy business, of course, and consultancy projects, and also we develop software which is comprehensive simulation environment called TCAE, which is software which includes several software modules. These modules are for meshing, for CFD, for FEA. There is also acoustic module for simulation of acoustic properties of flows. There is optimization module which helps engineers to run simulations in large or small in loops, which and iterate with the results towards the goals, and also other modules are on the way. TCA is extremely flexible. It's ready to be used in an existing environment or in for new users. So there are very many of usability options. TCA is unlimited. There are no limitations on number of users, job scores, so we can be sure that the users will use their resources to the fullest. It's based on open source. There's more than 60 open source projects included in TCAE, and we are ready to really use or make available what's available on the open source market to professional users in the industry. So it's our main business and main added value. Also on top of open source packages available in the market, we have invested more than 50 years of consistent development in a team to deliver this TCAE. So I guess the value of TCAE is obvious. TCAE is accurate. It can be used as a black box, or it can be used as a highly sophisticated, high-end software where the user takes all the decisions step by step. So it's always up to the user how deep to go into the rabbit hole or not at all. There are various options and ways how to use TCA. It can be used on laptop or on personal computer or on cluster or cloud or remotely from home or in Windows, in Linux, in batch mode or in graphical interface. So there's really a wide range of possible usage. We have available 15 benchmarks which are publicly available, can be used again and again transparently. There are more than 50 real tutorials based on real projects from our consultancy business, and we have really good technical support. The new release has been released some time ago, and the cornerstones of the future development is the optimization tool, of course, the opt, then the acoustic solver, and the new simulation module we are working very intensively on at the moment is called T-Base, which will help users to create their own surrogate models and work with their data. Yes, and this will be it. I was very much concerned to be in those 5 minutes which I just made. So I will start with the content. So I would like to recommend to every user with every engineering project to start with goals. Really, it sounds like a cliche, which is everyone says that, but everyone knows that, of course. But I really recommend to sit down, grab a coffee, and think about what are your goals. Goals are extremely important everywhere in society and in life, and especially in engineering simulations. You have to know your goals because you have to know where are you going. Unless you will never get there. So goals. You should think about what's your project nature, where it comes from, where you want to go with it. If your project is disposable one-off or whether you are creating a workflow, a long-term process. That's extremely important. You should know what are your expectations, what you expect, where your project takes you. Will it be shared with your colleagues, or is it just for you? Will it be repeated again and again or not? What's the measure of your success, of the success of the project? When it's successful, when it's not successful, and how do we learn? We are there. We made it. It's finished. Again, very important question, because typically all the engineering projects or the engineering simulations are done in iterations, and you can iterate and iterate, and you can always improve everything. And it's very important to know when to stop, when the solution is good or good enough, or when not. My very favorite talk is about the accuracy. So you should definitely you should know what is the accuracy you want to achieve, and what's the cost, what's the effort you're willing to spend to receive this accuracy. It's a very important thing. So always think about what is the accuracy you want to achieve, and what's the effort you would like to spend, what are the resources you would like to spend. This is my very favorite graph. It's not favorite because I created it, but it's favorite because it's true, and it tells pretty much a lot. It tells that the effort is growing exponentially with the accuracy. It means that with relatively few decisions, I say those are specific decisions, specific qualified professional decisions you have to make. You should be accurate with your decisions. So for example, with a few decisions, you can very quickly get to some level of accuracy, right? But then if you're adding more and more effort, you're improving your accuracy only very little, right? So the effort grows exponentially with very little growth of the accuracy. The plot means the plot shows for example, the blue line shows how accurate you are with how many decisions have been taken. So for example, if you take only 10 professional decisions in your projects, in your project, you are going to something like 10% of accuracy. Of course, it's a general graph, right? It's general graph to give you thoughts, to give a food for your brain to think about. By the way, accuracy means here the distance from the measurement. Basically, you know the game we play here. You know the rules and that you also know the joke that everyone trusts the measurement, but the one who did it, and no one trusts the CFD simulations, but the one who did it. The measurement is holy grail. So this holy grail we are chasing here is the measurement results. Take it or leave it, or take it or not. That's what's going on, and we are pretty cool with it. So the measurement is the exact results, and you're getting closer and closer with your accuracy in your project. But yes, there are specific decisions, professional decisions you have to make, you have to resolve, and problems you have to resolve. And after some time, if you're like 2% close to let's say to the measurement, and you want to get 1 more percent closer, you have to take really you have to improve a lot of things to get there. So it's really exponential, and you should know it's exponential, and you should think about it in this way. Okay, so accuracy versus effort. Always know your effort and always know your accuracy. Okay, I'll start with I'm in the middle of general thoughts about how to run simulation projects. So you definitely, if you're using finite volumes, you need to create the mesh, the simulation mesh. And here are some thoughts about that. So first of all, you have to have simulation ready geometry, which was the last webinar about. So I'm not going to spend much time about this topic. I only say I have a general case, which is a standard, very the simplest possible tutorial for TCAE, which is carved pipe. Sorry, so this pipe is a pipe, and where the flow flows through. So I can only show you that the simulation ready geometry is something like this. I will disappear the FEA and FSI part. We do not need it here. And in this example, I will just take a look and show that almost every engineering simulation project, a CFD project, has some combination of walls. So it has a wall, a rigid wall, where the fluid flows in, if it's internal aerodynamics, and external is similar, but we are talking here about the internal aerodynamics. But it's very similar. And there are some interfaces, typically the inlet and the outlet, right? So you have inlet, you have outlet, and the wall. And this is what we call simulation ready geometry, because it's a one component. So we call them components. The volumes, or later future volumes, we call them components. And you can play with the components. You can have many components connected with the interfaces. This tutorial is rather simple. So I have only one component. It's a carved pipe with the inlet and with the outlet. And technically, it's STL file, it's surface file, which has been exported from some CAD, engineering CAD system. So this is what we call simulation ready geometry. It's important that the geometry is watertight, waterproof. So it means there are no big holes, or preferably no holes at all in the geometry. So the flow could stay in, and we can prescribe the correct boundary conditions everywhere, and that makes the simulation complete, and we can run it. Okay, so you have to have simulation ready geometry, which was about which was last webinar about. Okay, so then you would need to start with the mesh. You have to have the mesh, and that's a process. You will split your basically volume into little pieces called cells, which helps you to run the simulation on it. So for such a case, I can show that we have system of components here. In other software, it would be similar. I have just one component, which is called pipe, and I say it's static. Nothing is rotating, nothing is moving here. It's really static, solid component. And yes, it has one wall. According to the STL surfaces, it has the outlet, it has the inlet, and for that, I'll take a look what I have in the presentation. I have to create full mesh for all components, yes. And yeah, for the mesh, I have to set very important thing. If we use, and we recommend it, but we never push it, but we recommend it. We recommend the SnappyHex mesh, which is highly compatible with TCAE and with OpenFOAM, and it's really useful. But again, we only recommend it. We never push it, so it's always up to the user whether he or her just load the ready-made mesh, a complete mesh, and start computing directly on the mesh. TCAE is ready for that. Or if you are creating the mesh, so we suppose the simple case, the typical case, that you create the mesh from scratch here. So we have a component which is consisting of watertight STL surfaces, and these STL surfaces are the volume is meshed in the volume with the background mesh, and you say how many times the background mesh is refined with respect to the surface, or how many boundary layers are considered in the case. So you can say it here. This is just a basic principle. You can refine the mesh, of course, many times, and sometimes you need to specify the point which is located in the mesh inside the component, which tells the mesh solver what's the inside, what's the outside, and that's something like a general principle. So we did in this pipe case, and couple of comments. The mesh size is super critical parameter and super critical number. So the size of the mesh, the number of cells that your mesh consists of, is extremely important factor on everything. It influences the speed of convergence. It influences the quality of the results. definitely concerns everything, and especially the amount of data and the simulation time. And simulation time is something which is one of the bottlenecks. I would say, if you asked me, the biggest bottleneck in engineering simulations is getting simulation ready geometry. The second biggest bottleneck is simulation time. Simulations take time. Big simulations, transient simulations, multi-phase simulations, accurate simulations, they all take quite a lot of time. We have to get used to it, and we have to know what we are doing and save every time and every resource possible. Let's take a look what next we have here. See, I always recommend in every project to start with small meshes. Play it small, play small game, and play iterations, and do a lot of iterations in the beginning, because you can always refine the mesh. It's very simple to refine anything, but it takes finer meshes take so much more time and effort and resources and everything. So again, go in iterations, start with iterations, because every engineering project typically is used in an iterative process. That's normal, because you always improve everything. But start small, start with small meshes. It saves you tons of your time, and also gray hair. Yeah. So it's this. Okay, it was just quickly on the mesh. I can what I can say, okay, we have some settings here. I can completely remove everything from the case, and I can ask the mesh solver to create the mesh. So it's going on here. It tells me yes, it's meshing now. The meshing process is running. It takes only a little while, so we can wait for it. So when the mesh is created, I can visualize it with this button. Yeah. Let me check. Okay, I will ask again. Can you show me the mesh, please? And what? Yes, it's here. So this is the mesh of my basic settings. So we are already looking at the mesh which has been created in the tmesh module, which ran basically all the necessary settings, writes everything down, and run block mesh and snapx mesh on it. And yeah. So on my mesh, I'm clicking. I don't know why it's so slow today, but okay. Fair enough. So this is my mesh. This is already volume mesh, which will be the object of my simulation. So it's quite rough, but I'm okay with it because it's relatively quick. So you have to have the mesh. And in today's webinar, Radek will show much more about how to set up the mesh, but I only say a couple of principles in the beginning here. To the mesh, it may look complicated, but it's not. Almost everything can be automated. Almost everything can be used again, and good. It's like neural network, right? You can use the best things in the future because you remember it, and it's the same. With riding a bike, no one is the best when rides the bike the first time, but next time and next time and next time it gets better and better. And it gets quickly better unless you drive or ride it. Without knowing you're actually driving it. It's the same with CFD simulations. There's always a huge chance that you will repeat the good positive outcomes and tips and tricks. So what looks difficult, it's not after some practice and experience. Okay, I'll just quickly comment on simulation setup. I will just quickly ask my colleague Radek if I'm still visible and you can see it and follow.
Yeah, definitely. Just
And
continue.
does it make any sense, the presentation so far, Radek?
Yeah, definitely. I'm
Makes sense.
making a notes and I will follow your steps
Yeah,
during my part. So
okay.
perfect.
That's encouraging. Thank you. And I will just say a few comments on simulation setup. So yes, again, you should think what are the outputs, right? What are the particular results you want to make out of the simulation, and all the rest of the settings is depending on what are your outputs. why you are doing. It's similar to goals, right? But with outputs, we mean here really the exact numbers, if it's efficiency or if it's pressure loss or if it's some torques or some visual expected or unexpected flow fields. So it's always important to make sure you know what you are going for, and in the phase of simulation setup to make the case ready for that. That's very, very, very important. You should decide, for example, what are your time options, right? So with time options, I mean, what's your, in the CFD settings, what's your time management, right? Whether you're going for steady state simulation or could go for transient simulation, or you can go for both you can initiate the transient simulation with the steady state simulation, and how many simulation points you want to simulate. With simulation point, here we mean a set of boundary conditions applied to the that lead to different results, right? So you can have, for example, in this case, I have 3 points. Perhaps I have 3 flow rates, 3 different flow rates. So the different points create characteristics and speed lines, for example, if the speed is the differentiator. So you should always make sure what's your time options. Extremely important. I would say it's perhaps the biggest simulation setup choice, your time options, whether you're going for steady state or for transient. In my case, I'm here going to do a steady state simulation, but in some cases it's necessary to run transient where the quantities change in time. Okay, the next thing is settings that concerns physics, solver, and turbulence, and similar stuff. So you should know what to set. Physics is absolutely important. So you should be able to say what's your fluid, whether it's incompressible or compressible, what's the reference density, what's the reference temperature, what are the reference environmental physics. Of course, you should decide the solver, of course, the numerical order, the quantities, the number of processors you are going to run, and sometimes down the chain you should decide the turbulence, what will be the turbulence model, what would be the turbulence approach, and that's a very typical question to solve. What's very, very important is boundary conditions. From our technical support over 15 years, we know that 80% of all errors are somehow connected to boundary conditions. So boundary conditions are extremely important part of the process. You should know what you are doing with your boundary conditions, and if they're physical, if they're relevant, if they're telling you things, because as you know, in CFD engineering projects, it's extremely important what's on the surface. In the volume, you have limited options what you do in the volume, right? Because the volume is the playground of Navier-Stokes equations. So the equations are set in the nature. So the volume is the volume is Navier-Stokes equations. Of course, you can set the dynamics in density and viscosities and everything, but that's the volume. But your real input is on the boundary conditions. Really, if you should remember one thing from this webinar, boundary conditions are critical everywhere. So it's important what you set on the wall. It's for every quantity. It's important what you set on inlet for every quantity. It's very, very important what you set at the outlet of your simulation domain for every quantity. You should decide what will be your post-processing in this phase. It's really important to know what to set and how to set in the beginning, in the setup phase, right? Because afterwards some information may be lost, right? Because not everything is being saved during the simulation for good reasons. We know everything, but we never save everything. So you should know what to save and what not to save. Yes, CFD simulation is typically an iterative process, right? Of course, if you are in a research mode, right, you're researching things for the first time. Of course, you always go in an iterative process. Sometimes later, as our clients know, in the production, you do more and more productive simulations and use it for your product, and you just run it as a tool. But not every time it's the case. But almost. Oh, not almost every time is endless possibilities what to improve in every simulation. It's never done, right? Simulation is never like finite process. It's a system which can be always improved, always something you can always do something better than last time. So you typically run iterations. Here in iterations, I mean iterations in running, run 1, run 2, run 155. And small meshes help. Small meshes help you to iterate quickly over your simulations and improve quickly. You should always, during the simulation, that's important, during the simulation, you should follow the basic laws that conserves. So the flow rates should conserve, the residuals shall ideally drop, and final results can be also followed. We can maybe show it, right? So if I run the simulation of which is TCAE, it's this. Okay, I will run everything because I'm not sure if there are several steps. So I have run all run process. So now it's running, and I guess yes, this case is a little bit special because it has also FEA part. So there's the outer part, which is a coating of the pipe, which is meshed with NetGen, and the forces are transformed to the surface, and we can compute the material stress and deformation. So it's a little bit more complicated, but still I see something is going on here. Yes, so the case is finally running and iterating. So we could show another window of view. So I could be interested in, for example, in line chart view, I would be interested in some quantities, additional quantities that are processed during the runtime, and we could take a look, for example, how the, I don't know, pressure drop looks like, for example, and okay, maybe why not? Yes, so this is okay. It's quite flat. It's quite flat in this case, but we could zoom things a little bit, and this is how the simulation is done already. Okay, so we have 3 points. So okay, no, the third point is going on here. So the third point, let's catch it. I'm going for it. Yes, here you can see this is the delta P total. So the difference in total pressure compared from at the inlet and to the outlet, and you see it's somehow hopefully converging. It's simple tutorial, so you can display things here. You can 3 sets of residual. You can see 3 sets of residual here. Yeah. So again, things may look complicated for the first time, but they are not. We should be patient and really learn along the way. And look what we have here. Achtung, there's an expert on the air, and I will ask Radek to hand over the presentation. I can switch. I will switch it.
Okay, thank you.
Okay, I will switch. I'm still not very much used to. Yes, you did it already.
Okay, I think you can see our web
We
page,
can see
right?
your screen, Radek.
Yeah,
Please go
perfect. Okay, thank you, Luboš, and I will smoothly continue with a thorough explanation of all the points of the workflow, including the meshing and CFD simulation. And let me follow up the previous webinar. Just for those who haven't seen it yet, you can go for the resources webinars on our web pages, and here you will find a link to the the recording of our previous webinars, so you can follow it, and I will smoothly follow up the previous webinar. So what we did, just a small recap. We take this small Kaplan turbine, the real solid shape of the housing, of the motor, including all the solids, all the parts which are not necessary for CFD simulation. So what we did the last time, we cleaned it. So what we have done, we get rid of all the solids and unnecessary parts, and we extracted just the wet surface, and also we have created the interfaces between rotor and stator, and between the extensions, for example. And then we have exported, generated, triangulated the surfaces, and we have exported the STLs. So today I will take this STLs. So I have put it here into this directory, and this STLs will be used to import and to create the simulation flow domain. So just to see the overview of all of them. So basically we have set of STLs exported, and what we do is that we use each set of STLs to create the set of components. So we will have more components to build our flow domain. So in this example, I have also generated this huge or large extension, which is somehow also useful to let the flow calm and to have a proper conditions, and for example based on the measurement or the setup. So for example, you just know the pressure at some points, and also with respect to the evaluation purposes. So for example, you would like to have evaluated the efficiency just starting on this elbow and ending on this outlet cone, what and etc. And also this will create additional components, and more components, more fun. So let me start creating the project. So I will start very from beginning, like you are starting the new project from very beginning. So I will open TCAE, and I will create a new project. So I will click here on new, create empty, and directly I can store the project on somewhere on my disk. So I will put it into this folder we will be working with today, and I will name it, for example, TCAE webinar Kaplan. So I will name it as this, and from now on all my setups will be stored within this folder on my disk. So first of all, we need to start to setting up the mesh. So let us follow the Luboš notes or Luboš items which he had presented. So first of all, let's somehow tell about the interface. So what we have here, we have the main project manager, we call it, which holds all the managing buttons. So to work with and to run the simulation, generate meshes, generate reports, etc. And here we can enable all the modules. So today we will work with the tmesh to setting up the meshing parameters, and whenever we will have the mesh and we will be satisfied with the mesh quality, refinement, etc., then we will start to setting up a CFD simulation. So let's go for it. Let's go for tmesh. So if you click on the tmesh, then you have new set of menus to set up the meshing. First small menu is the general. Here you choose what will be the output. So we will work just with the CFD application. So we are fine with the CFD mesh, but in the same way we can set up the FEA mesh or both. Here use external geometries. If you check this, then instead of loading the STLs into the project, you just tell the path to the STLs, and the STLs, the input geometry, will live outside the project. So whenever you move your project somewhere else, you need to move it together with the input STLs to, for example, create a new project or resimulate something. Otherwise, you will lost track with the input geometries. So if this checkbox is unchecked, so then the STLs are imported directly into the project and it lives within the project. So you can move the project anywhere, and all the results and all the information remains within the project. In general, all the modules can be scripted. So maybe we can also do a webinar in the future about the scripting. So using the scripting, you can modify the workflow in the thousands of ways. So it will give you more space and more options how to modify, how to include a specific functionalities which are not directly implemented, or your codes, or any treatment or modification of the geometry, meshing parameters, or whatever. And it also holds for the CFD simulation or any other module. So we click in this way, and now we can go to the CFD mesh, and let's start with the first menu. So here, this is the rotation reference frame, because we are working with the the rotating machinery. So we need to define the rotation, and the rotation is set by the axis of rotation. We have two, static and rotating, because also we can have a stator which has some rotational symmetry, like for axial machines. And whenever we have any periodic boundary conditions, this condition needs to know the transformation with respect to the rotational symmetry. So therefore, we have typically two reference frame. One is called static and will be used to define stators, and the second one is the rotating, to define the rotating regions and the rotation transformation. If I remember correctly, yeah, the rotation axis is Z. Yeah, so the blue arrow here denotes the Z axis. So we will modify it to Z axis rotation reference frame. And I think, yeah, our geometry is placed into the origin, so the rotation axis goes to the origin. Okay, so this is rotation reference frames, and now we are going to components. So now we will set component by component. So basically each component is meshed separately, so we can treat any component as a separate mesh. So we need to just focus on each component, mesh it, check, for example, if the mesh is correct, and then go for the next component. Whenever we have all the components set, then we need to take care about the connections, about the interfaces, and if all these are checked and generated, then we are done and we can go for CFD setup. So let's go with the component by component, and let's start importing the STLs. So let's go with the first component, which was the inlet extension. Inlet extension is just the pipe. So we have inlet extension inlet, we have a wall, and we have one interface which will be connected to the stator. So we have these three parts. Ta-da! We have it here. Whenever you load these STLs, it will appear in this table, and also it will appear in the render view. Anytime you can click on any part to see which part we are setting up if we are not sure. And what is also good is to click here, because the CFD geometry is held by this item. It can be hidden, it can be shown. And what I like is to set some kind of opacity, because if there are some object inside, I would like to see what is happening inside. And also, for example, for setting up internal point, which defines part of the meshing. So then it's also good to have the opacity to see if the point is put inside. So for each component, what we can set, so we can set a component name. So it's up to the user. For example, I can name it as inlet extension. Reference frame, static. Periodic geometry is in case we have just kind of, for example, periodic segment. So in some scenarios where we expect the symmetrical behavior of the flow, we can save some cells by cutting the axial domain like a cake. So we put just one part and preset periodic boundary condition, for example. But in this case, we will have it as a full pipe. So what we have here, type of the boundaries. So inlet. So we have a set of boundaries. I think for CFD engineering it's pretty clear. At least if you are doing internal flow, you have to have at least one inlet and one outlet from the domain. With respect of the component has to have some inlet and outlet. So if the patch is connected to the neighboring component, we call it interface. If it's not, we call it inlet or outlet. So inlet extension is the inlet, wall is wall, which is the default type, and interface outlet interface from inlet to the stator will be the outlet interface. Yeah, the naming I think is natural, that inlet denotes the part where the flow goes in, outlet is part where the flow goes out, and free stream interface is where we don't know the direction of the flow, or there could be in general both directions, something like if you have the propeller behind the ship or ship vessel, and you just need to put the propeller into the rotating cylinder, and the whole cylinder is the interface. So you can't. So there can be both direction flow on this cylinder. So for that scenarios, we set the free stream interface. But here we have the outlet interface, because this is just the extension to initialize the flow. We don't need to solve it as too accurate. So for example, we can keep all the refinement surfaces to minimum, and what we need to set is the background mesh cell size. So this is the largest cell which will be created. So I will typically we use the cube cells, but for example, I can show you how to save some cells on these extensions. So first of all, I will do in this way. I think the diameter of the pipe is something like 16 centimeters. So if I set just 10 centimeters, it's too large, as you can see. So let me start with the, for example, 1 centimeter. It could be fine. And following one of the Lubbock points, always start with a rough mesh. So make the mesh as rough as possible, but the mesh refinement has to be set in the way that all the topological shapes and all the details has to be captured. Yeah. So typically, if you do such a large meshing, I think it's not a good idea, because you will have just one cell or 2-3 cells. So I think it will be not possible even to mesh, but it must be to certain level, it must be accurate and well resolved. So let's start with 1 centimeter. For example, if you would like to save some cells on this part because it's not so important, you can uncheck the cube, and now you can set the dimensions of the basic cell size in any direction. So let's start, for example, with I think this is the Y direction, right? So we can make the double, for example, in this direction to save some cells. Okay, and the last important parameter to set is the internal point. So internal point is visualized by point. It's it's interactive, so you can take it and push it into the internal part of your component, or you can define it manually. So let's say I will adjust this diameter is just for the visualization purposes. So it will visualize just this sphere, which is nicely draggable, and we can push it or put it into our domain, or you can put it, of course, manually if you know the coordinates or dimensions of your components. Okay, so I will get rid of visualization of this outlet interface. So I think I am done here, so I'm okay with that. So I can I can I can disappear the internal point just to accidentally, I don't want to accidentally move it outside. And now, for example, if you have the first component set, you can save the current setup and just quickly you can build a mesh. Okay. Now, if you see it, okay, there is some troubles with my setup, so I can click here, check, and I think it will tell me, yeah, that I have the outlet interface which is not connected to any other component. So if I need to mesh it from now on, I can set it as outlet, go back, save my current setup, and now I can build the mesh. If you click here on the table TCAE output, you will see what is happening. Now, yeah, the mesh generation is pretty quick because there is almost nothing to do. Just create a background mesh and make the snapping. So if I show the mesh, as Lubos already shown us, surface with edges, so we can see the basic mesh refinement. So it's pretty rough, but the mesh is okay for the simulation point of view. From the accuracy point of view, of course, it's not the optimal, but for the first check if my simulation will be set up in a proper way, and if at least some results I will get, it's enough. And also for the webinar purposes, because I need to run the simulation quickly within the webinar. It will be pretty boring to wait, for example, 1 hour for the results. Okay, so this was the first component, and in the similar way, we are going to the next component, which will be more interesting. So let's visualize back the CFD input geometry. I will get rid of the mesh, and let's import the parts for the stator. So let's take all the stator parts and the interfaces. So interface from the inlet extension is this one, and the next neighboring component is the rotor. So let's pick this interface stator rotor STL. Right, perfect. So new set of STLs for the second component is loaded, and now we can do the same framework. So set all the parameters. So I can name it stator. Reference frame is still static. I don't need any periodic geometry because it's a full geometry. And let's go for the types. I will go back to component 1 now because it will be already connected. So I will click on the outlet interface, or I will set outlet interface. And for component 2, I will quickly set the type. So what we have here, interface inlet. So this is the interface inlet interface. Interface to stator to rotor. So to be able to mesh it before I add additional components, so I will set it as outlet. The other, I can keep it as a wall, or if for some kind of, yeah, I will keep it for sake of simplicity. I will keep it as a wall. Stator hub, everything is wall, and yeah, so the rest are the walls, rigid walls. Reference frame here, let's check. So this shaft which goes through the stator, so the stator is, I think, adjusted to the casing by the blades, and the shaft goes through the inner part of the stator to the rotor. So this shaft part, which it is physically rotating, so I can prescribe the rotating part outside the rotating component. So this can be done for all rotational symmetry parts or walls or patches. So in this way we have just this shaft, so we can prescribe rotation on this shaft within the stationary component. Now let's go for the refinement. So first, because before I will go for the refinement levels, let's set the background mesh cell size. So again, I will put as 1 centimeter, which was fine for the previous component. Now I keep it as a cube, in a cube shape. Okay, meanwhile I can directly put the internal point into my component. So let's check if, okay, it's too close to the shaft, so let's put it a little bit further, and yeah, now the point is inside. Perfect. And now let's go for the setting up the refinement. The refinement means, if I visualize the background mesh cell size or background mesh visualization, so every cells which will be intersected by one of these STLs will be refined up to the level we preset here. So let's go for it. So here we have the same refinement level in Z and Z and X coordinates. So the inlet interface, we can keep it in zeros. Okay, then what we can refine, for example, all the other parts. So let's go for the important parts. So let's set everything to level 2. Okay, and maybe this inlet duct we can also keep, for example, we can set to level 1, for example. Then what we have there, we have blade pressure suction side. So let's see what will happen if we keep it at level 2. And for example, blade leading edge, which is these small parts of the blade, which is highly curved. So for those parts, we can set higher level of refinement. And because they are small, we can keep the level same for as minimum and maximum. The minimum and maximum refinement level, if we set different values, for example 3 and 5, so the algorithm decides what level to put at the different parts of these STLs based on the local curvature. But in this case, because this part is curved as a whole, so we can set the same level of refinement for the whole part. All right, so I think we can keep it in this way, and let's try what will happen if we start meshing it and how the mesh will look like. So again, I can go back to the manager, I can click save to be sure that everything is correctly set. We can click the check. So project setup content again, interface. Yeah, perfect. So I have created the interfaces, but I haven't connected them yet. So the connection is done by right button click on the given interface patch, and then the menu will appear and it will give you a set of possible connection, and we have only one possible connection now, is to connect to the stator interface. So now it is connected, and the connection also can be checked here. If you go a little bit further in this menu and scroll down, and you extend this components map, so it will tell you how each component is connected to the other components. So now we have nice solid connection from the inlet extension to the stator. All right, so now again save my setup to be sure. I will check project setup is okay, and because I have changed the type of the boundary to the interface, so the first component has to be also remeshed. But we are fine because we haven't changed any meshing parameters. So now I will focus just on the stator. And what I haven't done, so anytime you can abort it, And to speed up the mesh generation process, you can also parallelize the meshing. So if you go back to the setup, to the last menu here, parallel run, you can increase the number of processors. My computer here has 10 physical cores, so I can set 10 cores. Again, save my changes and rerun the mesh generation process. Again, if you go to the TCAE output, if you set here output messages, you see what is happening on the background. And for more detailed output for the currently running task or solver, you can see the output. So this is the output of the SnappyX mesh. So for those who are familiar with the SnappyX mesh, you can follow all the log, all the details of the meshing. So now the mesh is almost done. Okay, and something was wrong, so maybe all right. As you can see, the mesh leaked out, so probably I forgot to include some part of the setup. So what I done. Okay, so I have all the parts, I hope. So this is the shroud, this is the shaft, inlet duct is okay, stator hub is also there, stator blade suction, part pressure side, leading edge, interface rotor stator. Alright, so now I'm not sure what happened. So the internal point is still inside, which is okay. Okay, the refinement was also fine. Okay. So, okay, so to be honest, I'm not sure what happened. So typically, what does it mean if you see such a leakage? So if you visualize the mesh again, so it means that the mesh was meshed from both sides. Yeah. So if I go just for the mesh and here to the multi-block, and I will just pick the boundary, so you can see, you can visualize each part of the mesh. So we have it there, but also we have this default patch which points that the mesh leaked out from our domain. So which means that the domain is not closed fully, or some kind of meshing parameters like internal point is put somewhere else than it should be. But in this scenario, I am not really sure what happened. So maybe I have accidentally took the different STLs. Okay, let me quickly check. So the inlet duct stator, right. So what I can do is to visualize my input geometry, and for example do a slice if I have enclosed counter. So what I can do is to make a X slice, for example. Yeah, this one, apply, get rid of the CFD. Okay, so I think everything is closed, right? If I get rid of the first one, okay, all right, it seems fine. Maybe, I don't know if the export was okay. Okay, so interface rotor to stator, inlet duct, or maybe the mesh. Because, okay, let me try it to make it a little bit rough, because I'm not sure if I took a proper STL. Maybe if you can see it, I have some troubles here, so I'm not sure if I took a proper STL. So we have some local, yeah, if you can see it now, we have some holes in there. So maybe I took a wrong STL, but let's try to fix by a little bit, make the rougher mesh. Just as an example. So let's regenerate the mesh with a little bit rough setup, but the main point is that I should go back for the STL generation and check what happened here, right? Why this, you can see these holes at this surface part. Okay, let's check if now the mesh will be better, and if not, maybe we have some other option how to heal it implicitly, but let's wait for the result. Okay, all right, and now it's meshed properly. Okay, so there is some trouble. Okay, go back to the multi-block inspector. No, sorry. CFD mesh and visualize the whole mesh. Okay, so now it is correct. So I have some troubles on the input STL. So definitely when I will go for the refinement, I should recheck the input STL and heal the errors in the input STL. So okay, so this was example how to tackle with some errors in the input geometry, and this again emphasize what Luboš mentioned, that the crucial part is to have ready for simulation STLs as the inputs. Okay, so this was nice example, an unexpected example of the bad STL meshing quality or STL quality. And I will quickly go for the other components in this example. So let's go for the rotor. So again, I will import the rotor STLs. So interface of the rotors and STLs of the rotor. Let's import them. For now, I will get rid of the CFD mesh, and I will show the CFD geometry. So now we have this part. What I can do again is to set the component name as rotor. Let's go for the interfaces. So this is the rotor outlet. So I will set for now as the outlet. Here I will set it as outlet interface for the stator because I can directly connect it to the interface from the rotor side. And now right click, connection to the stator. And as you can see now we have nice 3 connected components. I will keep all as a walls, and reference frame here. I need to care mainly about the wall boundaries, and here so all the walls here like hub, excluding the shroud, will be rotating. So all these parts which creates the impeller should be rotating, but the shroud is static, right? So it's so-called unshrouded case. So shroud is not rotating, only the impeller and steels of the rotors are rotating. Before I go for the refinement levels, I will again set up the cell size for the background mesh. And for example, because the rotor part is the most important part and the main flow patterns are happening there. So for example, I can set finer refinement or finer cells on this level to have also the finer cells in the volume, not only on the surfaces. In the same way, I need to set the internal point. Let's put it inside. So just if you are putting it manually, so just you need to change the views to adjust the point in the inside the rotor part. Just check if the point is not, for example, in the hub or in the cell in the blade. But I think now it's pretty much okay. Yeah, here in the flow, in the blade passage here. Okay, so it's placed properly, and go back for the refinement level. So what I like is that the mesh refinement on neighboring interfaces is homogeneous, or not homogeneous, but has the same sizing of the cells. It makes sense because you interpolate, or internally the quantities are interpolated on these pair of interfaces, so it makes sense to have the same refinement from both sides. So on this rotor stator interface, for the stator part, we have level 2 and 2. And because we have refined the overall cell size twice here, so we have we set a half of a cell size on the stator side, so I can set just the level 1 because it will be comparable. It will have a comparable size from the rotor side on the interface to the cells on the interface from the stator side. Again, for the blades, let's quickly set, for example, as an example, I will set the level 2 everywhere, or maybe, oh sorry, because I have set the half of the cell size on the stator part, so I will set everywhere 1, including the hub and shroud. Okay, and let's see what will happen. Just as an example, that if this refinement will be sufficient to mesh the rotor section. And I hope I set everything. Not, I haven't. I forgot to set the reference frame for the whole component, which is important for rotating part. So I'm setting it as rotating. Okay, now let's click save. Let's try to run the rotor side meshing, and whenever it is done, let's visualize it, and I think we will see that the mesh will not follow all the detailed part. So this is crucial when you are starting. Whenever you generate the mesh, immediately visualize the mesh, because it will tell you a lot about the meshing. So as you can see, there is a better refinement level for meshing this gap between the rotor and the stator and the shroud. And for example, to see the overall meshing for the blades, so you can again click on the CFD mesh. I will get rid of all parts, and I will show just the parts of the rotor. So for example, or blades and the hub. So you can see both that the leading trailing edges are not well resolved, and the main problem is that the gap between the blade and the shroud is also not well resolved, and you can see such flaws in the mesh, which generates a very bad cell parameters, which can finally, during the simulation, which can lead to the divergence or crash of the solver. So we need to go back, and we need to refine the given part. So let's say I will just refine the leading and trailing edge. So I will increase the level of refinement on the blade leading edge or on the blade trailing edge. Therefore, if it's possible during the STL generation, it is good to split really these parts into separate parts. If it's possible, it's not crucial, but then it will help you and give you more freedom in setting the refinement locally. Yeah, otherwise, if you have one STL for the whole blades, then you need to set, for example, the levels like 1 as a minimum and 2 or 3 as a maximum. And then, of course, the solver, the engine, the meshing engine will decide where to put the lowest level of refinement or the highest. All right, and the last one is the blade cap. We have also splitting of the blade cap, so now we can set level 2 for the meshing the blade cap. Going back, clicking on save, and regenerating the rotor mesh. All right, so this is the standard scenario of mesh generation for the new geometry for your new project. So go step by step. Let's start with the rough parameters, low level refinement, high sizing of the cells, because you will get the mesh quickly. You will be confident, or you will learn the shape of your input geometry. It will show you where the problem could be during the meshing. And oh, sorry, I click build. I need to click on show. So now what you can see that, okay, so the leading edges are better, but not the best. But I think that still we have the problem on the shroud. So if I click on the CFD mesh, and I will also visualize the shroud. So still we can see that, yeah, there are big flaws and bad regions, bad cell regions in the gap between the blade and shroud. So again, I will, for now, I will just increase the level of refinement for the blade cap, and I hope finally we will have a good mesh which we can use for the simulation. So let's run our last iteration, and if the mesh is okay, then we can add the last component and we are ready to go for the CFD part. So as you can see, again, you need to iterate, you need to go step by step. What is good that this component thinking will give you a focus on a certain part, and you don't need to take care about everything within one shot, but you can go step by step over over each component. And right, so as you can see, okay, I will here, if you click on this icon, it will reset the view and also reset the view rotation point. So sometimes it's good to re-click this reset view button. So if you can see now, there are no holes in the shroud. So it means, I think the better visualization is that if you get rid of the surface with edges and visualize just the surface, and now you can see now a nice smooth shroud without any problem. All right, so I think the rotor part is fine. And last but not least, maybe just to speed up, I will just add the outflow, and I will be not adding the outlet extension. So let's go back to the T-mesh. So let's go here, and I will add the last component, which will be the outflow. Import, and let's go for the outlet. So outlet hub, outlet wall, and interfaces. So interface rotor to outlet, and the last one will be the interface outlet to outlet extension, but I will set it as a final outlet. So this will be pretty quick. So you can see the extension just includes the interface, the hub part of the rotor, and the outlet wall. So this part is static. Interface outlet to outlet extension will be the physical outlet. I will go back to component 3. The outlet I will redefine to outlet interface. Rotor outlet is the inlet interface. Immediately I will connect it to the rotor, and hub and wall are the walls, but the hub is connected to the rotating impeller, so I will set it as rotating. The background, my cell size, I will set back to, for example, 1 centimeter, and I will refine just the hub. I will refine the inlet interface to the same level as on the rotor side, including also the different sizing, of course. Therefore, 2 outlet wall, I can keep it Okay, I will set 0 just for speeding up the simulation. I think it will be okay, and the outlet will be also not refined, so it will have the dimensions of the background mesh cell size. The last what I need to put is the internal point. Okay, it is directly at the outlet, so I need to move it a little bit inside. Nice. And I hope everything is set, so let me check. So I will save. To be sure, I can click check. Okay, connection is done properly, and let me build the last component. And whenever this component is also meshed properly, we can, for example, we can generate all the components again, or all the components which were changed, because I have changed the outlet to the always to the outlet interface, so therefore I need to recompute it, but I will do at once at the end of the T-Mesh workflow. And okay, CFD mesh is yeah, it was here. Sorry, what I have clicked. Yeah. Okay, maybe I need to go to the multi-block. Sorry, because I have clicking a lot here. Yes, of course, and I will click on everything just to see all the parts, all the visualized parts. And okay, but now, right, I visualized already all the parts generated, and when I visualize it as a surface with edges, nice, so we can see, okay, it looks good. There is no flaws in the mesh. Just to be sure, I can make a slice, what is happening inside, just to see also the volume inside on the slice. Again, surface with edges. So here we have our topology. So okay, what is important, that all the parts important are meshed properly, so it has its own shape, and we don't see any troubles, any holes in the geometry. Here we can see that also the gap is refined, so we have some volume there. So this is a good good setup for the first safety simulation run, and whenever everything is running, then we can start refining the mesh and looking how the results changes to obtain uh, the result with better accuracy from the mesh parameters point of view. All right, so everything we have done. So meanwhile, I will remesh everything to have also the final mesh, which is then on the background imported into the CFD section and used for the CFD simulation. All right, so this was the meshing, and now I can enable the CFD setup and quickly go through the CFD setup. So typically the CFD setup is much more simpler to set up from the time frame point of view, because we just set the parameters of the fluid, we set the boundary conditions, etc. So we don't need to iterate and waiting for the mesh generation. So this is what I meant. So let's go for the CFD setup. In the general section, we have the simulation type. All the simulation is always tailored to the given application. So here we have the application of hydro turbines of the Kaplan type. So we have a type here, hydro turbine. So we can choose this one, and this will modify some setups which are tailored just for the hydro turbines, and also it forced the report to include all the important parameters which are typical for hydro turbines, including the efficiency formulas, heads, and other quantities. Let's go for the physics. So in the time management, we choose the the solver time management, if we would like to go for the stationary or transient simulation or both. So for the initial simulation, we will go for the steady state, which is much simpler, faster, and for 80% of applications, it's enough and good and accurate enough. If you need to go for to resolve more complicated flow patterns at unstable conditions or whatever, then you need to go for transient. So let's stick with the steady state. Speedline is a set of simulation with a fixed rotation speed. So this Kaplan runs at 1500 RPM, so we need to have just one speedline. Speedline points mean how many different boundary conditions you would like to simulate within a single run. So typically, if you need to resolve the efficiency map, so basically this number is the resolution of this efficiency map. So if I set, for example, 5 points, then the 5 points will be simulated and I will be able to set 5 different boundary conditions, typically 5 different flow rates or 5 different pressure boundary conditions at the inlet and at the outlet. The number of iterations, so it's the maximum number of iteration which solver performs. It depends again on the application, on the complexity of the of the machine, on the mesh refinement, and many other parameters. So typically, if you start refining the mesh, and if, for example, if boundary conditions are far from the best efficiency point, then you need to add or increase this number of iterations. So for this purpose, for example, we have a pretty rough mesh, so I will set 1000 iteration as a maximum for each simulated point. Fluid properties, here you set the property of the water here, or you can use some custom fluid parameters. Let's stick with the water. You can use fluid defaults, which are set to the water at 20 degrees Celsius, I guess. So if you need any additional parameters, you can adjust them here. Rotational reference frame. So here you set which rotational reference frame will define the rotation. So therefore we name it as rotating. So rotating component will be rotated and all the physics, and it will be modeled as rotating region. And here you set the rotation speed. So the units we can check, we can choose our RPM, and it operates at 1500 RPMs. Just a typical mistake is the direction of the rotation. So it follows right-hand rule. So if my thumb points along the z-axis, so my cross fingers define the rotation direction. So as you can see also from the blade definition on the stator, so in this way the impeller rotates. So therefore it's a positive value for the rotation. So the positive value is okay. Within the multiphysics, you can define some additional physics to be included into the simulation. So here typically for the pump and hydroturbine application, we can ask for evaluation of the cavitation risk. So it's just the post-processing tool which evaluates the pressure and compare it to the pressure of saturated vapor value. And if the pressure is below this threshold, this saturated vapor pressure, then it denotes these cells and creates some statistics above these measurements. What the parameters should be set. Cavitating patches means these patches will be used to evaluate how many proportion of the surface on these patches are affected by cavitation. So typically I would like to include all of them. Maybe I will just exclude the shaft. So I need to have all of them to be included in the statistics. The low pressure patch means the pressure at the lowest side which is used for setting up other additional cavitation parameters. So typically for hydro turbine is the outlet. So I will set the outlet interface, which is this one, and the high pressure patch is typically the inlet patch or the patch which is of the interest. So maybe I can set this elbow, the inflow into this elbow part. So it will be, for example, the second one. All right, so this from this point of view, cavitation is enough to be set here. Turbulence, you can choose any model you prefer and you are confident with for the given application. For the simulation, number of processor is the same like for the T-mesh part. Here you can adjust the numerics. So numerical order, second more accurate, less stable, first more stable, less accurate. But typical for this pump and hydro turbines application, the second is stable enough and will give us very accurate results. If you have some special format or special shape of cells, like from external tools which have some high non-orthogonal property of the shapes, you can enable this non-orthogonal mesh schemes, which are more diffusive and keep the solver stable during the simulation. But it's application for this kind of non-orthogonal meshes. Runtime evaluated quantities. Here you define what you would like to see at the end of the simulation, besides the main quantities like pressure, velocity, turbulent quantities, and other. You can ask to evaluate some other quantities. The averaging window is used to average the solution because still even it's steady state, so every iteration can oscillate because of the property of the solution and the conditions. So it's important to have a nice converged, stable, constant solution at the end, and this averaging window is additional stabilization of the instant quantities. So again, it depends how big are the oscillation and how the case behaves. So based on this, you can adjust the averaging window size. By clicking here, you can simply enable what quantities you would like to additionally evaluate from the simulation. Efficiency probes define the quantities for the report, basically from which parts the torque will be evaluated, pressures will be taken, etc. So typically the inlet patch is the patch of the interest where you can measure or you would like to take the average pressure and other quantities. So for example, because this inlet extension could be some kind of artificially set just to initialize the flow at this part, so we can choose this interface, the second one. So basically this interface will be used as for evaluating the pressure at the inlet. Torque patches, typically you choose all the patches which are rotating. So basically all the patches here listed in this table or in this list. And outlet patch again can be chosen either the outlet or directly at the rotor, just to evaluate the efficiency of the rotor itself and exclude some losses of this diffuser or whatever. But let's keep the outlet as the outlet interface. Of course, you can add more efficiency probes if you would like to evaluate it from different interfaces, etc. You can also add some additional forces patches if you have some specific objects on which you can explicitly evaluate the forces acting on it. Then you can list it here. Just you will edit. You will choose on which patch you would like to evaluate the forces and other quantities connected to the forces, and the probes. You just define the coordinate of the point in which you would like to follow the given quantities. So simply, it's simple as it is. All right, I click somewhere else. Now we can go for the convergence check. So this is the checking criteria for stopping the simulation before the maximum iterations are reached. So for speeding up the simulation. So you can tell, okay, my main quantity is the efficiency. So I can choose, for example, efficiency average. And if efficiency average value is doesn't change more than this tolerance over the averaging window, then the simulation can stop before the maximum iterations are reached or the predefined number of iterations are reached. You can choose absolute. So for example, if my tolerance value is 0.1%, then I can keep it in this way. So this is in absolute. Or it can be relative to the current value during the simulation. In the controls, there are parameters connected to the numerical solver and to the numerics in general. So these are the parameters connected to the relaxations, some bounding limits which can stabilize the solution in the early stage of the simulation. So just check it if the range is wide enough to include all relevant physics. And then there are some tolerances of equation solvers and other parameters connected to the solver iteration, but this is the numerical solver, this iterative solver for solving the system of linear equations. Again, scripting can be included in the same way as in the T-mesh. So if you would like to evaluate some specific quantities or any special, it can be scripted via the Python interface. And now the main part, so setting up the boundary conditions. So here, now the question is, what is the goal of the simulation? What are the known parameters? And based on this, you can choose a proper combination of boundary conditions. Typical combination is flow rate and pressure, and the second one could be the pressure and pressure-like boundary conditions. So here, so this is kind of a little bit artificial, small shaped Kaplan turbine. And what only information I found that it can operate something like at 10 meter and at 10 meters head approximately. So I can choose the pressure, total pressure, static pressure boundary condition, because I am not aware, I don't know the flow rates at which it operates, but I know the head. So I can set the total pressure at the inlet and static pressure at the outlet, so fixed pressure at the outlet. And for example, I can tell it by the bar units. So I will set bars, and I know the pressure at the outlet, so it can be set like atmospheric pressure at the outlet. It go out from the piping, for example. So I set 1 bar, and at the inlet I can vary the pressures to achieve something around 10 meters ahead. So for example, the middle point could be something like 2 bars to achieve 10 meters ahead. And just to reveal what is happening around this point, I can say higher head for the first point. So typically it's best to start from the higher flow rate, so higher pressure difference, and going to the lower pressure difference. And for example, 0.7 and the lowest. So I don't, if I set pretty low head, so it will not work, I guess. So let's try this minimum pressure difference for the simulation. What we also need to is how to initialize the turbulent quantities. So one of the options is to go for turbulent intensity and hydraulic diameters, because we are in pipe. So I think this is the option number 1. Turbulence intensity, typically we set 5% for internal flows. Hydraulic diameter is the diameter of the piping, which is 16 centimeters here. And reference velocity depends on the flow rate, but I know it because I ran it before, and it's something like 100 up to 200 liters. So if you have this hydraulic diameter, radius is 0.08, squared is 64, and P is something like 3 for the engineers, right? So we have something like 0.02, and if I divide it by the flow rate, we will get something like 10 meters per second, the average speed at the inlet. All right, the next are the walls boundary conditions. We will keep in default here, but the options is if you refine the mesh up to the very fine level, you can go for low Reynolds wall function, or if you would like to mimic some roughness, which can be also used, so you can set the rough walls and set the roughness based on the sand grain roughness, like the granularity of this roughness on the wall, and roughness constant is typically set to 0.5. But in this case, let's stick with the standard slip. No slip wall. It means a wall with friction, and this is the default setup for all the walls. So you don't need to care about the other wall parts, but you can set different boundary conditions for the specific part of the wall domain. Then we have interface conditions, so how to treat the information from one side of the component to the neighboring component. The default is AMI, which is a simple interpolation on the interfaces for some application and axial and symmetrical flows. But I think at this elbow side, the flow will be not symmetrical. We can impose the mixing plane, but mixing plane somehow uh, expect or impose symmetrical behavior of the flow. So we will stick with AMI here in this application. And the last but not least is the initial condition. So we have to set some initial guess from which this solver starts. So the pressure at the outlet was 1 bar, so I will set it to 1 bar. Velocity at the inlet, I'm not sure. So for example, I can set this -5 meters per second or -10, which corresponds to my expected flow rate, but it's not so important. It might be some meaningful values, and the turbulent quantities I can initialize by the inlet values. So this is from the simulation point of view, was all the parameters we need to set, and the final is what we would like to see in the report at the end. And we can also set some specific turbomachinery visualization, which are automatically evaluated and put into the report. So here is blade to blade view and meridional average. The setup is pretty simple. You will just set on which part of the domain you would like to see it, what is the hub, what is the shroud, which are important to be set to generate blade to blade views, and in general to create the transformation to the blade to blade view. And the meridional average is pretty similar. Here in the report, you can choose the section which you would like to see: efficiency, torque, head, power, cavitation risk, if defined. So I will keep it as a default. So all are there, and the unit into the report. So for example, volumetric flow rate, I think it's more human readable if it will be in liters in this for this setup. And so you can choose your favorite units to see, and these are some additional operation you can do for some extra specific evaluation and exports, typically to some additional post-processing in different tools, or to be connected to additional tools like external FEA solvers or any other solvers. Okay, so I think I'm too long, so let's save what we have said. So let's save it. Now I will click with the fear on the check button, and let's see. Okay, and perfect, because I have enabled the cavitation risk and I haven't set the custom saturated vapor pressure. So if it's not set, the vapor pressure is automatically evaluated for water at the given temperature. So to be automatically evaluated, the saturated vapor pressure for water, I need to set the reference temperature. So for example, reference temperature will be 10 degrees Celsius. All right, I will click save. I will click check, and for now, I haven't seen, project setup is okay. So keep fingers crossed, and now we can run the simulation. So I can hit run all button, so it will do all the steps which are not yet done. So because the mesh is already generated, it will directly jump to the solver, and now it starts solving our simulation with our boundary conditions and our CFD setup. Just to quickly mention what we can follow. So as Luboš mentioned, we can follow the residuals. We can follow any other quantity which is available. So you can open the new, for example, line chart view. You can go here to the TCFD section. You can enable the quantities section here. And now if you go to the display, you can choose your quantity to follow. So I will go, for example, for efficiency. Then if you click to this view, you can again reset the view on the efficiency. And because sometimes at the beginning of the solver, the values are a little bit wild, so you would like to focus on the more relevant. So you can, for example, you can do it by mouse clicking and dragging the mouse, or you can zoom automatically to all the values and manually, for example, adjust the left axis range. So for example, we can focus on values between 0 or 0% and 80%. And this is what you can see. So the way of following the convergence is looking at the residuals and mainly looking at the goal quantities like efficiency or head or flow rate for this type of simulations. And if the values are calm, not oscillating, and going to the constant value, then this is exactly what we need, what we would like to see for any CFD simulation, that our goal quantities converges quickly and nicely without any oscillations. All right, so this was a quick CFD workflow overview. So as you can see, the first step is to generate a mesh. We always suggest to have a rough mesh, set up a CFD simulation, and then run the simulation, because this will tell you pretty quickly. You don't need to wait for the results several hours. You will get the results pretty quickly. And if something is, if I go here, and if something is going wrong, you will see it immediately. So sometimes, for example, bad boundary condition combination is set, so the value goes out, or efficiencies. So efficiency is, for example, negative, even the residuals looks good. So it typically means that something is wrong with the boundary conditions or fluid properties, etc. And whenever you will get what you need, so the result will be in the range you expected, or in the range it should be. So then you can go back for the T-mesh part, try to refine the mesh, and you just change few parameters and you run one click the whole workflow again and go for more accurate results. So this was from my side, from the mesh and CFD simulation setup. And I think here I can end, and for the next webinar we will start at this point to visualize the results, to play with the visualization, etc. Right? So I already heard Luboš.
Yes.
So we can go back
Radek.
to Luboš and
Thank you very much. It was really interesting. I followed you carefully. Yes. So let's keep on your screen here, because I would like to ask the audience to ask your questions. It will be a Q&A. So ask your questions. Those brave who stayed with us almost 2 hours. So ask your questions, and we will do our best to answer them. And I think we haven't any questions yet, but it's, or do we have some? Yeah, we have a couple of questions. Sorry. We have a few questions. So anyway, Radek, just one question from me which just popped up. when you when you're happy with your results because everything is being evaluated during the simulation, right? So when
Mm-hmm.
you would be happy with the results, would you comment if you can stop the simulation and get the results you have, or skip points?
Oh yeah, yeah, definitely. Good question. So about the management, which I didn't mention. So during the simulation, you can manually manage it. So for example, if I see, okay, at the moment the efficiency is converged well, so I can click, for example, skip point, and now it automatically skip the rest iterations and will go for the simulation of the next point. If I would like to see, for example, the instant values, which we show next time, right? You can click to write the results at this point, and then I can display them. And if I want to interrupt or stop the simulation but later continue with the simulation, I can click quit and write. So it will store my immediate results, and later I can continue with the simulation. So this is the quit and write. And if something is wrong and I need to restart or redesign or modificate some parameters, I can abort and discard the setup because I don't need to store them. I will redefine some parameters, and I can run the whole simulation again with the new CFD parameter setup, for example. And
Yes.
last but
Mhm.
not least, for example, you can, during the simulation, you can generate a light report, which will tell you the basic information about the simulation during the simulation. So you can, for example, open the new HTML view, wait for the report, and then the report will appear even during the simulation with the currently simulated data. And the last one, at the end of the simulation, I think I have somewhere here, you will see the full report. So you will see something like this. So HTML view, HTML report with all the relevant and important parameters uh, in the format of the tables and graphs. So you will see the efficiency performance map, the instant values, how it converged, the final values, and it holds for any other quantity which which are evaluated. Yeah, including the, for example, cavitation risks, how many cavitating volume or cell were cavitating, cavitation index, and other quantities. But I think this will be a topic of the next webinar.
Yes. Radek, okay, so I'm starting to look at the questions. We haven't many of them, so this one is quite important. So, a client is asking whether how you control the mesh layers, the inflation layer in the mesh. If you can, maybe you
Mhm.
did already, but if you can just quickly comment what are the parameters where you switch it on, and what are the basic parameters of the inflation layer and
Okay,
layers in
okay,
the mesh near the
perfect.
wall.
hmm Let's go for it. Maybe I skip this because I'll have a little bit delay with uh, with the meshing of the stutter part, with some kind of problem with the STL quality. But about the layers, so the layer can be edited pretty straightforward. So for any wall type patch, you can simply define how many layers you would like to add. So for example, 5 layers, and the parameter of the layer itself is defined in the advanced meshing option section for given component. So any component can have different parameters of the boundary layer. And if I go for the component 2, for which I set these 5 layers, I can go for layer mesh parameters, and here you can set expansion ratio, the thickness of the first, final, or whole boundary layer, and other parameters. Relative sizing, if it's relative to the cell size or if it's absolute. And in this way, you can adjust the boundary layer for any ball patch with its own layer parameters. and then it's automatically added during the mesh generation.
Yes, Radek, yes, this is good. Thank you for this. Yes, the people typically ask about this. There was another question. A related question to this is someone is asking whether you can change the configuration, because not everything from the OpenFOAM and from SnapAX Mesh, not everything is included in the graphical interface of TCAE. And the obvious question is if you can change anything on the disk or in the case manually, and if it's taken into account later in the simulation.
Okay. So all the changes has to be done via the interface or via the scripting, because the program behind the C processor is managing the whole process. But for example, what you can do, you can generate the whole project even with the results, and then you can go on the disk into the project folder, which is, for example, here where it's here Kaplan, into the simulation run, into the TCFD, or if you would like to play with the mesh, into the T-mesh, but typically into TCFD, into the stationary solution. And here, this is the OpenFOAM case. You can touch as you want, right? So you can adjust it, but then you need to run it manually for those who are familiar with OpenFOAM. And in this way, it can be handled.
We would say it's possible, but it's not recommended. That's how I would classify this operation. So it's possible. It's not recommended. And for conceptual changes, we would rather recommend to go via scripting, right? So you can write down a short script and say what quantity in which dictionary would be changed forever in the workflow if it's not possible directly in the graphical interface to be saved in the configuration files normal way. So this is how we would proceed with this. And because time is running very quickly, we are already 2 hours long. Yes, also a question about the internal point. Yes, this is correct. So someone it's a more a remark. The project configuration does not save the radius and the origin of the internal point. So yes, that's the paraview property of default property, and it's not being saved with the project. Yes, so you have to change it every time you open the project. So we are sorry for this. And by the way, in the next version we will have something which helps really a lot. There will be automated internal point function which will cover 99.9% of cases. So there will be no need of specifying manually the internal point, which is typical bottleneck and annoying little thing. So from the next version there will be hopefully no internal point needed, only with a little few exceptions, which is not important. Okay, Radek, I'm going to we're going to conclude basically, because we are already very long. So I need to, if I find it in this new user interface, which is sometimes difficult to me because my name is here, Team CFD Support, I will make myself presenter. So I'm doing it. And
I think you need to share the screen.
I need to share it again. Okay.
Because I don't see anything.
I'm sharing, so I hope you can see it. Yes, so this is again the expert window. Thank you, Radek, for everything. It's been detailed work. This has been the Q&A session, and this is it. This is really it. So I would like to thank everyone who attended. Feel free to come back anytime. We will gladly answer everything. We are here for you. It's our job, and we like it, and we decided for it years ago, and we still like it. So thank you everyone, and see you sometime somewhere. Thank you. Bye bye.
Thank you. Bye bye. Have a nice day.
Yes. I think that something is going on here, right, Radek?
Yeah. Everything is recording, I see.
The recording has started. Okay, so yeah. So let's keep it professional from now. So yeah. Well, what we have here today is CFD post-processing webinar. What do we do is everything like usual, right, Radek?
I hope so. I hope so.
On my clock, it's 1 minute to 2 p.m. So hopefully we start on time. And let's see. I'll take a look. We already have a couple of attendees here. Yes. Okay. So again, I will start with general introduction and everything, and I will when I'll run out of my ideas and energy and everything, I will switch it over to you, and you will just show
what
the
I
real
can.
stuff.
Yeah.
Okay.
Sure. And maybe anytime the attendees can ask, right, for specific visualization, for
Yes.
example.
Before we
If
start,
they have
I'll try
limited
my best
time.
to say it again, but
Okay.
this should be as collaborative and open as possible, because the CFD post-processing is a huge topic. We realized it this morning when we started to make preparations for the webinar, and it's a huge topic. There are a lot of details and everything, and it's difficult to cover it in the whole concept. So everyone should be asking questions, and we'll be happy for that. So we'll take it quite easy today. So what's on my clock? It's 1 minute over. So we'll start the webinar. Okay, so I need to switch. Yes, switch it here. So hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you our knowledge and our experience with CFD post-processing. Today's webinar is part of the series of webinars. So we 2 webinars back we had CFD Preprocessing webinar, and then we had the next one which was connected, which was called CFD Simulation Setup. And today's webinar is continuing the process and the workflow, and so it's called CFD post-processing. So welcome everyone. Make yourself comfortable and think about what you need in your projects, and tell us, and we'll be happy to answer. So today's webinar will be hopefully dedicated to your questions and our answers. So we are happy to answer your questions, and we'll do our best to show everything what we know about, or how we do, or how we feel, how we understand the philosophy of CFD post-processing. The webinar is being recorded, and the recording will be later made publicly available to anyone on our YouTube channel. So feel free to hang on. And what else? Together with me on the line is my colleague Radek Maca. So let's check the connection works. Hello, Radek. Can you hear us? Can you see us?
Yes. Hello, Luboš, and hello, the audience. I can see you. I can see the presentation. I can hear you. So I think everything goes well.
Okay, thank you.
Yeah.
So I think we can start. So hopefully we have everything covered. So I would like to ask the audience to make it easier for us. Ask your questions. Ask simple questions. How did you create this image? How did you create that? Really ask about anything, and we will do our best. Okay. So as mentioned, sorry, I guess we will switch the cameras off like usual, Radek, right?
Yeah, sure.
Yeah, because it gives, I believe, better aspect ratio of the screen. Okay, so as mentioned, we created this webinar series. So the first webinar was about CFD about CFD preprocessing. So we recommend it. It's on our YouTube channel. The next webinar was CFD simulation setup, and today's webinar is this CFD post-processing. So we will continue with what we are explaining in the whole workflow. So it can also serve as a education materials for those who start with TCAE or OpenFOAM or these open source workflows. So it's definitely recommended. The agenda of today's webinar is this. I will start with the necessary introduction, but I promise I will be short. Then we will continue with general thoughts about what we think about post-processing, and then we can also discuss principles and general thoughts, and then we have a couple of examples where we can discuss typical examples and typical way of work and typical workflow points. And at the end, there will be Q&A session dedicated to your questions and our answers. So feel free to ask your questions. All the questions will be answered. The most representative questions will be answered right away in the webinar. And the I would say specific questions will be answered later via email, but you can be sure that all the questions will be answered. So I think, yes, we can go ahead. So very quickly, CFD Support is a company located in Prague, Czech Republic, 15 years on the market, hundreds of industrial projects delivered, and we are currently creating software which is actually it's already on the market. So we are developing software called TCAE, which is in fact a comprehensive simulation environment where the users can use open source, OpenFOAM, and other open source pieces to run engineering simulations. TCAE consists of software modules. They're independent and they can be used in individual work schemes. It depends on every engineer and on every business and user how to use the workflow. It's extremely flexible, it's extremely automated, and we believe it's ready for industrial projects. The beauty of TCAE is there are no limitations on number of users, jobs, or cores. It's really unlimited in every way for just one single license for every business or for every unit. And there's a wide range of licensing and collaboration options as well. It's based on open source. It means that it's built up on open source, which is a huge benefit because here at CFD Support we have mastered the ability to integrate open source pieces and turn them into professional software for the industry. That's definitely a big benefit. So we are quite small company that know how to use open source and develop on top of open source, which is big benefit because we do not need to develop every detail from every piece of software, but really we built what is successful already and we make it even more successful. So that's a huge added value. Our software is focused, it's accurate, and it's automated. And it's available for a really wide range of using options. So it can be used remotely or, of course, locally. It can be used on laptops, desktops, clusters, clouds. It can be used remotely from home or from the office or in the office. It can be used natively in Windows or in Linux, in batch mode, in graphical interface. The workflow is very consistent and well tested. So we believe there are a lot of usage options for everyone. It's been tested many times. There are 15 public benchmarks that are transparent and repeatable anytime. There are more than 50 tutorials, which are, again, of course, available, and we have quite good technical support to make sure that everything works smoothly. Current stable release is 25.3. We are, of course, working on new versions. For the future, we will definitely focus more and more on optimization, which we believe is a big trend and paradigm shift on the market and in the industry. And also we are developing our acoustics module. We believe it's a quite big deal and unique capability of our software. And for the future, we are definitely developing a new software module which is called T-Base, and it's going to store all the data about your simulations and about your product and help you to make smart decisions using surrogate models very quickly. Okay, so these are our future developments. So we are excited of all of it, what's happening out there and in here. And I would start with my general thoughts or our general thoughts about post-processing. Radek, I would like to ask you to interrupt me anytime if I say something what you would like to complete with your thoughts. You are very welcome. So I'll go with the post-processing is extremely important stuff, right? Because you are turning the numbers into valuable insights, right? So it's extremely important because I would say it's a final step of large expensive workflows of large process, right? So you do all the stuff from geometry creation, cleaning, meshing and setting the simulation, running the simulation. Everything is extremely expensive, and finally when you have the results done, when the results are simulated, then the post-processing comes, and it's extremely important because when you do something wrong at this last final step, everything what has been done before is ruined and wrong. So even if you do everything perfect and you do poor post-processing, everything is poor. So extremely important final critical step. Visualization is one part of post-processing, right? To make it visual, to visualize the fields and everything is one big thing. It's a huge strength compared to, for example, measurements. Typically, physical measurements are measuring something in single point or points with some probes, and the information is incomplete. There are, of course, other benefits of measurements compared to engineering simulations, but definitely a big advantage of the engineering simulations is having the whole information about all basic quantities everywhere in the simulation domain. It's a huge advantage. So visualization is really part of post-processing and really important. But of course, the images does not mean we have an understanding. There's a huge difference between the visualization and the interpretation of the results, right? So we can visualize them, and if we visualize them correctly, we have to learn to read them, to understand them, to interpret them well, and that's the value we can be. Then we can get the value out of it. So that's important to realize the difference between, okay, we made something visual, but where's the value for us, right? What's the lesson to be taken? That's really important. We use ParaView. That's definitely we think it's really great tool, which is it's open source. It's really great tool that helps visualizing the fields, the quantities in space. That's really great, and not only this, but even in fact so much more. So there are, sometimes I say there are endless visualization possibilities. You can take a look. For example, I guess you did, but still you can take a look on, let me see, on our website. Anything what you can see on our website has been created in ParaView. So all the visualizations were created in ParaView. Also, I would recommend to take a look on our YouTube channel where we upload quite a lot of stuff. Again, almost everything was created in ParaView. Maybe maybe you can take a look on our Instagram or something. But anything what you can find there, that's my point, has been created in Paraview. So Paraview is extremely strong and free tool for engineering data visualization, and that's why we like it. It's when we talk about post-processing, it's important to understand the kind of data, right? The data details, what we are looking at, what are the sorts and the groups of data, what we are what we are observing. So I guess you know that there are scalars, scalar fields, there are vectors, there are derived quantities. So there are there are some basic quantities which we simulate, and that are the real results of the simulation. And then there are derived quantities. There are so the volume fields, they live in the volumes, right, in the space. There are surface fields that they live on surfaces, which are typically flow rates or fluxes, for example. So that's the group of visualization, right? To see it, it's sometimes really important. And one big group of post-processing quantities is integral values, right? It's again a valuable contribution of engineering simulations, that the one big group of results is integral values, right? So that they are stored somewhere in CSV files, in some tables, that where you can see those various averages, various quantities that define the whole state, right? So those are numbers again, but really representative numbers what we wish to see. So for example, torques or some forces. So I would say in every CFD project there are some forces, right? You always look for some forces in various forms, of course, but integral values are extremely important. As mentioned in previous webinars, again, everything is about goals. Your goals are something which is incredibly important, because the goals, they define everything. They define success, they define what's good, what's bad, what they tell you what you are looking for. So always, and of course as well in post-processing, you look for your goals. Every project, every simulation, every engineering simulation has its nature, right? Sometimes it's research, and in research you often look for the existence of the solution and for the visualization, for example, while in the standard tests you have run million times in the past, and you just run it, you just use it as a calculator. Yeah. So then you're more likely looking for integral results, right? So it's always about goals. That's definitely my point. For a little while I'll switch to Paraview, or I mean, this is TCAE, which is our software where you can set up the simulation, you can run it here, follow the convergence, and evaluate the results. So pretty much everything you have to create the geometry somewhere else, but the rest of everything can be done here in Paraview, in TCAE, which is its home is made of Paraview. So yep. So I have a simple tutorial, which is our tutorial of Kaplan turbine. And what I would mention here, those are really, I would say, just the basics, right? Sometimes it's difficult to start with Paraview. So I'll only mention a couple of basics that maybe what's for me very important is the views, right? So every time you open a new view, which is called layout, or you can rename it, of course, but by default it's called layout. You open the views, right? And you can say what kind of data representation you would like to see. So often we have this 3D CFD connected with 3D geometry. So for that, there's definitely the render view, which is the basic view in Paraview. I personally quite like this item view. Maybe I will try to open this one. And in it, I can start visualizing the geometry. So there are a lot of options for these views. I would like to okay, I will go ahead with what is offered in ParaView. So these views are extremely important. You can of course have HTML view, you can have line chart view, you can have plot matrix view, you can have really spreadsheet views, you can see the tables, you can see pretty much anything, and you can create your views. So it's definitely very flexible, and yeah, it's open source anyway. So yeah, so the views, right? There are a lot of views, and yes, also the line chart view can be this, right? You can follow the residuals, or you can follow the efficiency, right? So that's the line chart view, for example, or you can watch some statistics in HTML view, right? So there are views, and these views they are like basic interpretation of the data. It can be 2D, 3D, or spreadsheets or whatever. Then I would like to mention that there are sources. You can with sources you can actually create things. So you can add I would say individual components to your data visualization. So sources. Then there are filters. There are a lot of filters you can use. So you can really play with them. There are a lot of filters. Some of them are very often used. Some of them are always used. Some of them are rarely used. But there are a lot of filters which you can apply on your data, and you can play with your data. I would like to definitely mention that the basic filters which are typically on your panel with these shortcuts, the calculator, contour, of course, clipping, slicing, thresholding. You can extract data. You can use vectors, glyphs. You can use stream tracer to follow the paths, and there are a lot of really interesting filters. I'll go ahead that there's also geometry representation where you can follow, for example, the plane surface, or you can follow view it with for example, you can view the mesh with the edges, or you can see obtain various other representations in points or in edges, etc., etc. So that it's this. And the next what I would like to talk about is you have different panels which are really important too, because in your pipeline where you have your items, that's the pipeline browser, you have your items there, and each of these items have each of them has its properties. Extremely important panel where you can set everything, its definition. You have panel view where you can see set the, I would say, the colors. In the display panel, again, very important. You can follow various forms of again the data representation. So I can maybe quickly click here that I like this call front face, back face representation in back face styling in the display panel where it helps me to look inside, because it basically it hides the it hides the front faces of the object, so you can look with it inside the object, for example. But it's just an example. There are a lot of visualizations everywhere. So these panels are extremely important. Display also information tells you, for example, the size. So this one is huge. It has something like 50 meters in X direction, and last but not least, but the last one is multi-block inspector. Again, very, very important guy, because you can split your model with it into pieces, and you can very easily look at what you want to look at. So these are panels. And what else? There is endless possibilities what you can display. Maybe if you would like to ask about anything, you can help us. You can create such videos like this, for example, in ParaView, because you can open multiple views. You can add multiple text options and the colors and everything. So ParaView is really really complex. And here I would maybe hand over the presentation to Radek. I will only finish with the last point I would like to make, is that almost anything is possible. You have to know your goals, definitely. And the last point I would like to mention is it's all about the experience, right? If you're first time in ParaView, it sometimes may look difficult, because there are a lot of options that are not directly, I would say, clear from the beginning. So sometimes it takes some time, but when you learn it, you will be totally happy with ParaView, because it offers really, really complex and detailed post-processing options. So yeah, I will hand over the presentation to Radek. I hope I will find where to do that. Let me see. Yeah. So yeah, no. Well. Where do I do that? Radek here. Make presenter. Yes. Here. Yeah. So we've got it. So Radek, can you?
Okay.
Are you following?
Yes, I'm carefully
We,
following.
we can see your screen,
And
Radek.
okay, perfect. Great. So thank you, Luboš, for the introduction and general tools which we can find in ParaView. And I will smoothly continue. So first I will quickly introduce the post-processing tools, or to check the results we have directly from the TCAE simulation, mainly the integral values. I typically say that the integral values which are automatically processed and averaged and integrated are the can be understood as the general properties of the case. Yes, with efficiency, torque, pressure difference, etc. And then the visualization is to interpret the local properties, so you can zoom, you can visualize any quantity you need, pressure distribution on the blades, or flow separation around the blades, yeah, to visualize streamlines, visualize glyphs, etc. And also one of the most important part is to have a nice visualization of the results to present to your bosses, to other departments, to have a nice and overall view on your case, on your project. So first of all, let me start with the with the TCAE and the direct output to be post-processed and to be, let's say, to read and understand. So first type of the output is the HTML report, which summarizes all the results and all the case you have just simulated. So the report includes the standard information. I will be very quick because I think we have mentioned it several times during our previous webinars. So you have the simulation statistics, you have the basic, let's say, view on the convergence. So anytime you see something weird graphs which are not which are oscillating heavily or not going down, but mainly going up. So I think you will directly see if the results are meaningful. here, or if something very wrong happens during the simulation, like the simulation diverges or any other stuff. So this is the first view, which tells you, okay, if the simulation is okay or not. Yeah, you can go for analyze if, for example, your y plus goals and other parameters are okay. Then there are several these integral values like the head, efficiency, and others. You can always follow the final results. It means the results at the end for each simulation point or simulated points. For each efficiency, you also see the convergence, which is the blue line. The red one is the averaged value. So you can also check if all the quantities converged well. Typically, if the average value reached the constant state. So this basically holds for any any part of the or for any section in the report. So you can carefully follow all the quantities and for example create your first impression, the first analysis of the results, compare it with previous measurements or previous results, and basically this is the most important part, I guess, because this is what at the end what you need to have, the parameters of your machine in terms of efficiency or local properties like the power, torque, or pressure at a given part of the domain. So this is, let's say, the summary of all the integral quantities that are evaluated automatically out of your simulation. So this is the first. If you need any advanced post-processing, or if you need to evaluate any specific formula for, so for example, if you don't want to evaluate, for example, total efficiency, and you would like to evaluate from the static pressure, for example, not from the total pressure, then you can go into the project folder on the disk. So this is, we have it here. And then if you go to the simulation run, into the TCFD, and you can find all the quantities which you find and many other quantities which you find in the report in the CSV files. So for example, if I go, as I said, into the TCFD folder, into the post-processing, sorry, not post-processing, but to the stationary or transient, if you are simulating transient case, then here in the stationary, you go for post-processing. Then here you have several folders which stores the integral values. So let's start, for example, with the efficiency, which includes the most information about the results. And here always we have a couple of files. First is the efficiency, which stores all the information for all time steps or iterations. So you can also plot your own convergence graphs for all the quantities, but mainly we are interested in the final values. So anytime you just double click and you can open it in your spreadsheet view, so in Excel or LibreOffice, and you can find all the quantities, and you can quickly create plots or define your formulas to evaluate specific quantities based on this. So you have total static pressures, you have you have the differences, you have the pressure ratios, you have the magnitude, velocity, magnitude, and other quantities on the defined inlet and outlet from which the efficiency probe was evaluated. So this depends on the topology of your case. So if I go back just to see the topology, so for example, here we have this Kaplan turbine, this tutorial turbine, and it consists of, if I count properly, of 5 components. And on any interface, so on both sides of the components, on the inlet and on the outlet side, we have also the integral values automatically evaluated, and you can find them here. And so each of this folder refers to the interface on the given component. So if I would like to see what are the values, for example, at the outlet from the stator part, from the green one. So I think we call it stator. So we have these two, stator from inlet extension. So this is this interface, and we have here stator to rotor, which is the outlet interface. So if you go in, then we have again a couple of files, and in the interfaces final now we have the quantities, the integral quantities of total pressure, static pressure, flow rate, velocity magnitude, and the circumferential and meridional angle, if it makes sense to evaluate. So again, here you have the pressures and all the quantities, which again you can read, you can copy out into new spreadsheet folder with combination with any other interface, evaluate your specific pressure differences or whatever, and again to process some quantity which is important to evaluate for you to analyze the case. Yeah, so this is basically all the integral values which are very important for CFD engineers, because these values basically define the performance and the main flow parameters of your simulation. So these are the integral values. And then if you would like to go to study the local properties of the flow, or evaluate visualizations, and for example compare some specific part of your simulated domain or of your machine with previously simulated case, with for example, if you are studying and for example optimizing the shape of the blades or any part of your domain, then you can visually compare what are the differences of pressure distribution, or for example the flow separations at the given parts. Then you can nicely go for the loading the results and visualize the results. So you have two ways how to visualize the results, as Lubos already shown us. First one, directly from the TCAE project. You can click here, you can create a new layout with the render view, and you can click here, you click here, display the results, and then choose what part of the domain and which quantities you would like to see and be able to list in the render view, and consequently also visualize. So this is the first one. But whenever you are just, let's say, playing with the visualizations and you don't want to play with the project itself, so you can anytime go on your disk, open new TCAE session and load just the results, which can be quickly done. For example, just going into the case, into the given type of the simulation. So again, here stationary, and you can open this TCAE result.foam, and automatically the results are loaded into the ParaView and can be processed and visualized by standard ParaView visualization tools. Okay, so let's do it. Okay, so I will load it just to see the flow domain and the results in my render view. Okay, make it full screen, and let's go for it. So first of all, ParaView offers you to combine any results or any object with any other object. You can fill the pipeline with the sources, filters. You can apply the filters on any item for which the filter can be applied, and to save the memory, because for example, I would like to combine the visualization of some slices of the volume mesh, and to this, I would like to add just the surfaces of the blades, for example. To combine, to see the blade surfaces together with the slice, etc. And so one option is to visualize, for example, just the hub of the rotor. So you can list or just the rotor surfaces, including the blades and hub. So I will uncheck the internal mesh. So now you can see I have just the surface of the rotor. But to this I would like to also add the slice somewhere through the volumetric mesh, through the volume, right? So one option is to open the new foam file to load the data, but this time in the memory I have loaded the results twice. So from the memory point of view, it's not the best approach. So what I can do is to, for example, I will load all the items and of course all the arrays, all the fields which were evaluated. So I will load all of them to load all the data I have available. And then there is a filter which is called extract block. Yes, it's this one. And I think there is also the icon somewhere if I'm right. Okay, I don't see it here. Yeah, it's here. So this one, extract block. So you can click on this icon. And first, okay, I would like to have one item for application of the slices and all the filters for on which I need to apply on volumetric mesh. So I will check just the internal mesh. Okay, so this will be first extraction, right? And I name it, for example, volume. And I will do the second extraction just to see, for example, the surfaces of the stator, blade, and the hub, for example. So I check only the stator shaft, for example. I will skip the shroud because I would like to see the inside and I don't want to block my view by the shroud. And the same I will do for the rotor. And I think there is also the hub which goes to the outlet component. So let me click these parts. I will name it surfaces, for example. Okay, without misprint, surfaces. And now if I visualize just the surfaces, I have a nice view on the surface. And what I can do now is, for example, I would like to see a slice just to visualize, for example, the contours or the streamlines on a slice going somewhere in the middle between hub and shroud, for example. So I can create a volumetric sorry, I can create slice. So as you see, first you need to click on the item on which you would like to apply a filter. Then you click. So this right now I would like to apply slice. And here in this properties panel, you can adjust the slice properties. So for example, now I would like to do the cylindrical slice, which is aligned with the z-axis, which is my rotation axis. I will align to the center, to the point 0, and the radius I will decrease to the radius of my hub or shroud. So I will put somewhere in the middle. So now radius 0.055. Now I can click apply. Sometimes it will throw you this warning about splitting the VTK polyhedron function, which somehow split some weird shape cell, for example, but it doesn't affect the view, but sometimes it will throw the error, so you can just ignore it. So I will click here to disappear the slice selection, and now I can, for example, visualize the velocity contour. And for example, what I would like to see is the relative velocity on the rotor side. And now, for example, now I would like to apply the surface LIC filter, which will nicely visualize the surfaces. But because my domain is pretty long, I would like to cut it. So on this slice, I can apply the clip. I would like to clip it by the plane which is perpendicular to the Z direction, and I will move somewhere here. And now I will click apply. Right, so this was the other half. So I can click here, invert the clipping plane. I can disappear the show plane, and this is my slice, for example. And now I can visualize, for example, a surface LIC. Yeah, it takes some time on this computer. I don't know, maybe because the graphics is not so powerful. So now it computes the LIC filter, which is the, I don't know the abbreviation, but basically it will visualize the streamlines on the surface, as you can see. And then you can play with the visualizations. For example, you can color it not by pressure but by velocity, etc. But it really takes a long time on this computer. So this is one quick representation of the LIC filter. But for example, as you can see, the streamlines look weird. So I think it's because it's evaluated based on the absolute velocity and not relative velocity. So if my computer goes quicker, you can click on the display, and in the display section, yeah, here perfect, there is a section for definition of LIC properties filter, and here you can switch to the relative velocity, and now the relative velocity is automatically evaluated, and in the rotating component it automatically evaluates the relative velocity. So what you will see is that in the stator parts the streamlines remain the same, but for the rotating part the streamline will follow the blades lines or whatever. So like you are sitting on the blade and looking on the flow. Yeah, so as you can see. All right, so this is the first visualization and basically the combination. I will get rid of this LIC filter because it really slows down my computer. So let me uncheck the surface LIC filter and go for simple surface visualization. And maybe then let's go for additional filters to show you. All right, so this was the clipping. You can see you can combine with every, for example, wireframe, and really you can combine with other filters. So let's go for it. So for example, what we can do is to create what I like, maybe if I see the nice surface, is to create a pressure contours. For example, it's a nice visualization. So first of all, what we have here is the pressure in kinematic pressure. So which is the pressure of which is the default mode in for incompressible cases. So the pressure is the relative pressure divided by the density, so so-called kinematic pressure. So for example, to see it in the real pascals, so you can apply the calculator. So on the surfaces, yeah, exactly. So I would like to apply on the surfaces. So I will apply the calculator, and the calculator works in a simple way like the other calculator. So first you will define the name of the new field. So I can call it pressure instead of just P, and the pressure will be calculated from the available scalars or vectors, but I would like to compute it from the static pressure. So to to transform it to the pressure in Pascal, I need to multiply it by the density. So it was density of water which we set. So it was 998 kilograms per cubic meter, of course, and then we would like to add the reference pressure which we set, and the reference pressure was simply the atmospheric pressure. So I'll calculate this. All right, now we have, as you can see, the new pressure values. So it's here, and I can scale it to reasonable values. So there is some Okay. All right, I'm fine. So, okay, I will focus the best way to focus somewhere and use this eye view. All right. So, but still the values looks weird. So I'm not sure what was the original values for the pressure. Okay, but never mind. Maybe I will just put wrong values which do not follow my setup of this case. But in this way, you can transform the pressure in the pascals, or you can play with any transformation of your quantities to the new one. So I will let's go back to the pressure, for example. So now what you can do is for creating contours. So first I will rescale my view to some range I would like to see. So for example, I don't want to see just the minimum pressures of this. I would like to see nice, let's say, contours and the region. So let me, for example, try this one. And to keep the scaling you set here, you just need to uncheck this enable automatic rescaling. Because if you for example, go for the next point, it will automatically rescale the quantity. So I don't want it. So I would like to keep the values in this range, right? So for example, okay, this looks nice. And to create the contours, what I can do is first going here into the color palette browser or panel, which can be enabled here by this edit color map, right? Also color map editor. So if I get rid of it, so you will enable it again by this icon. And here is the number of table values. So for example, I would like to see just 20 values. And always here you have two variants of value representation. The first one is with this box, which shows you the value in the cell or on the face, as you can see. So if I add the surface with edges, you can see that the constant value for each face, while the pressure with this point is interpolation to the vertices of cells or of faces. So if I switch to this P, you can see nicely smooth, more more convenient for contour visualization. So I will keep it this. And for example, to enhance the boundaries of each contour or of each constant section of the pressure, you can create the contours on it. So I will apply on this calculator. Uh, you can apply the contours, and now you need to set a specific range. So the specific range needs to follow your legenda or your ranges of the given quantity. So you can set, for example, not for example, but in this case, minus 500 and 300. And because we have chosen 20 contours, so 20 sections, so we would like to follow the edges, we need to have 21 contours. So I will apply 21, and after applying it, it will create the contours, but not of the pressure, but of the static pressure, right? Perfect. Maybe I will color it with a native with a constant color, and I will enable visualization of my pressure distribution. And for example, the contour, I think the color black will be much better. Perfect. And now you can see now nice pressure contours with the boundary enhancement. And again, for example, now I would like to make these contours thicker, so I can go to the display, and here line width, I can set larger number for line width. So now we have nice pressure distribution and the counter visualization. Yeah, that's perfect. And for example, to visualize also the flow into it, we can visualize the streamlines, the volumetric streamlines. So this can be evaluated pretty easily. So I will click on the volume because streamlines, I would like to visualize the streamline not on the surface, but in the volume. So here I will click on the volume, so the extraction of the internal mesh, and now I can apply the filter streamlines, which is this one, so stream tracer. And if you go to the properties, you define the stream tracer. So stream tracer or streamlines are defined based on some random seed of the points from which the streamlines are evaluated. You have two options. First, to create a source by the line. So for example, if I place, sorry, so I need to place this line into my volume. So for example, I will visualize also the volume. Here you can click display just to see only the contours, for example, or not contours, but to see the domain boundaries. And the streamline tracer needs to be placed somewhere, so somewhere where it cuts your volume. So for example, just by an example quickly, so put it somewhere inside, and this line will create the seeds for defining the streamlines. So there are additional properties. So line is here, and resolution means how many points are generated on the line. So let's start with 500. And for the other options, okay, I would like to apply on the velocity vector, and okay, I will keep it in default just to quickly see. So first, you see that it creates the random points on the line, and through these points, which are placed within the volume, it will create the streamlines. What you can see that on the interfaces, it disappears. The streamline disappears. So we can switch here the interpolator type not by point locator but by cell locator, which will improve the streamlines going through the interfaces. So basically, the stream paths are not evaluated based on the interpolation to the vertices of the cells, but it sticks within the cell centers where the value of velocity sits. So it much better follows and follows the interfaces and go through the interfaces. So this is the first option. The second option is, instead of line, you can use point cloud, which means that you define the sphere. So it works in a similar way. So you create this random seed by the volume of this sphere. So you will again put somewhere into your domain. So I will start with in the inlet pipe. You need to decrease, for example, the radius, right? Yeah. So as an example, it will be fine. Again, click apply. So now it will create the random seed of points within the sphere, and from these points, the streamlines are visualized. Right. So this is, let's say, the simple way of streamlines generation, but there are of course some advanced options. So I would like to show you. So for now, I will disappear my streamline generation, and for example, now I would like to have a nice streamline which goes through the, for example, stator. So what I can do is that based on the volume, I can create a slice. So let me show you. I will create a slice which go through the stator, for example, here. Sorry, I will zoom. Okay, so somewhere here, all right. So now I have a slice, if we can see it. Yeah, maybe I will move it a little bit further from the interface. Okay, apply. All right, this is fine. And basically, this slice is also can be interpreted by the set of points, and also these points can be used as a source for streamline generation. And for example, there are many points. Basically, it corresponds to some intersection of the cells and the boundaries of the cells and the vertices of this intersection. And just to, for example, make this raster more coarser, you can use another filter which is called, I think, mask points or something like that. Yeah, mask points. And here you can see the mask ratio. It means how the coarsening of the points which are available there. And you can choose, for example, the random sampling. And if I click apply, I don't know if it will be visible. I need to go back to the points and generate vertices. Sorry, I need to generate the vertices. So this is my new, let's say, point cloud, and this was the original one. So you can see we get rid of every second point maybe. So if I increase this ratio number, so I can make it even more coarser. And now I can use these points to create a streamlines. So for these options, there is a filter which is not streamlined, but streamlined stream tracer with custom source. So we can apply it. Now the input is the volume, because I would like to generate the streamlines in the volume, and the seed source are my mask or the slice, but I would like to apply on the mask to get the the seed points more coarser. So let's apply it on it. And now if I apply this filter, so now it computes the streamlines which goes through all these points. And maybe still there are many points, and after it we will see nice streamlines going and be more equidistantly distributed through the sections we have chosen. So in this way you can more sophisticated, or in a more sophisticated way, you can create the streamlines for your cool visualizations. Yeah, perfect. So this is what we have. So nice streamlines, and maybe I will switch back to the cell locator, and to have a nice streamlines also on the rotor section, I will switch to the relative velocity. And now we will have a nice visualization of the streamlines together with the pressure contours in our tutorial Kaplan turbine geometry. And basically, in this way, you can combine any visualization with any other filter, like glyphs or any other, basically. So what are the main output of this example is that you don't need to load the results anytime you need to evaluate or visualize new part of the geometry. So do it just once. Load all the parts which you will need for the visualization, and then extract each part by the extract block, on which you can then apply either, for example, a streamline tracer, or just for visualization the surfaces and for example the pressure distribution. Okay, so streamlines are loaded, and now, for example, you can play with the visualization of the streamline. So we can go to the display, and we can color it not by the pressure, but for example by the absolute velocity. Okay, for each you will have the legenda, but you can get rid of the legenda if you need. And I will just scale the velocity, I think up 30, for example. Okay, looks nice. Now what we can do is to add the line width to be more thicker. So as you can see. And what I also like is this visualization option to render the lines as tubes, which gives the view more a plastic view of the streamlines. And what is also cool is to apply the opacity on the streamlines. So if I have enabled the streamline tracer here, and I can click here enable opacity mapping for surfaces, and you have nice visualization. Yeah, of course you can change the opacity by adjusting this graph, opacity graph. You can change the range of the for the velocity or pressure to combine to achieve your favorite visualization, etc. Oh, and of course you can choose the different representation of the coloring, so you can apply any other favorite palette or preset colors. So let's go for example this one as an example. All right, so this was the example of combining any filter with in combination with any other filter. All right, so I hope if you have any question what to visualize more, so please put it into the into your question section in the webinar application. And maybe now I can show you some additional visualizations, maybe a little bit advanced, but I think still clear. Okay, what I didn't mention, I can show it right now. So this is my, let's say, preset view. I would like to keep, for example, for other results, for other visualizations. So what you can do is to go to the file, to click save state, and save the state into the file. So for example, my state, or yeah, let's keep it my state. And anytime you would like to reproduce the same visualization and maybe on other results. So typically you run a little bit different simulation with, for example, adjusted geometry. So you can open the paraview again. So I will open the plane paraview. And then, okay, it's already here. Okay. Now I don't want to play with the manager, with the TCAE project, so I can delete it, and I can click here just to load state option, locate my my saved state, and here if you like to use the same results, you can keep it as it is, or if you would like to switch to another result of the same topology geometry, of course, then you can locate it and click on the given form file. Okay, and the same visualization should be loaded, and you will see basically the state where you save it. So this is good to keep track with what you have visualized. And for example, sometimes if you put a lot of filters, maybe sometimes it's memory hungry, so it can crash the paraview because of memory leakages, for example, or basically because your all memory runs out. So then it's good to time save the state to keep your working backup. All right. Okay, so now it loads our visualization we have done. Yes, perfect, it's back. So you can see that it nicely works. And for example, what I would like to show you next is some additional example of a little bit different topologies. So here I have run some transient simulation of the external aerodynamics, very simple case. So let me open it. And let's show what we can do, for example, in terms of visualization of turbulence, which is pretty demanded visualization for external aerodynamics, but not only for external aero, but also for internal, if you would like to really see. And if you have the transient simulation with DS, turbulence modeling, or LES, but I think it's not even not possible with regular resources. But with DS, you can run a nice transient simulations where you would like to focus on the turbulence and, for example, visualization this cool wakes behind your object or whatever. So let's load it in the same way. So again, I will load all the parts. I will load all the quantities, and let me quickly show the basic visualization. Okay, so this is a simple virtual tunnel or arrow tunnel with the obstacle in it. It's a simple cube, and we have simulated in the standard way. So we have, I think, something like 20 meters per second at the inlet. Maybe I can show you the slice, what is happening inside. Okay, I can show you the velocity, and I have simulated 2 seconds. So if I go on back at the end of the simulation, so you will see some nice turbulences behind the obstacle. And now what I would like to do is to somehow visualize the turbulence. As you already mentioned, but I haven't opened it. In TCAE, you can ask for evaluating vorticity or Q criterion, which is one of the main main fields for visualizing turbulence. So what we can do is basically we have the volume and we have these fields. So we can evaluate or visualize the Q criterion and vorticity. So let's visualize both of them. So again, because I would like to combine the volumetric data and apply some filters on it, and also to visualize the obstacle itself. So again, I will split it into parts. So first I will create just the internal extract block, and additionally I will do also the, for example, minimum wall. So this is the bottom of the virtual tunnel, and the obstacle itself, which is this part. Right, so perfect. So this is my geometry and this is my volume. So if I apply the contour on the volume, I think this is the best way for visualizing the turbulence. And first I will apply on Q criterion, for example, and let's try value 10. So this will create the isosurfaces of the quantity Q with the value 10. So you can see nice turbulence eddies visualized by this by the quantity Q. On the surface, I can keep it, for example, as a simple color, for example, with white. And what I can do with the contour is create display, click display, and decrease the opacity just to see more what is happening also in the middle of the domain, etc. Okay, to this, for example, I would like to add the same visualization, but not for Q, but for vorticity. So I can split the domain, click render view, and for example, I would like to focus, or first what I will show you, I will create the same visualization. So first, this second extract block, perfect, with the solid color, with the white, and to this I will add the contour, but for the vorticity, if I have it, okay, good. Now, because I have the vorticity, sorry, where? No, extra box, sorry. Yeah, I need to visualize it, and then I have here only the vorticity, which is the vector, but the contour can be applied only on scalar. So first I need to compute the magnitude of vorticity if it's not already computed. So I will create new array name, magnitude vorticity, for example, this way, and then I can apply the magnitude on the vector field vorticity. So it will calculate the magnitude of vorticity, and now on this I can apply, I can use this mag vorticity to create contours, and I don't know, again I will try to put the value 10, and perfect, and this is the contour of vorticity. And now, because I would like to have the same view, I can right click on one of the render layout. I can click here link camera and click to which render view I would like to link cameras. Okay, and now if I am changing the camera position, it's changing for both views. So in this way, we have the pressure contours, pressure vorticity contours, and what we can do now, of course, play with the visualization again, changing the opacity, for example, to the same level as for the previous one. For example, we can switch to different color, okay, to distinguish these two quantities. What you can also do is to, for example, add the current time to be visualized and later to be viewed in the animation. So you can click annotate time filter here. Perfect. Now I can see the time, and for example, you can also add filter or the source, as Lubos mentioned already, and you can add a simple text, and for example, name it as Q criterion, but not in this way. So we need to go up. So here it is Q. In the display, we can put it on the right corner, for example. And similarly here, we can create a new source with the text and, for example, name it as vorticity. Okay, or magnitude to be more precise. Perfect. And now, if you change the time frame, of course, the particular data will be loaded. And to create the animation from it, you can go here to File, Save Animation, check create the name of the animation, test animation, for example. Okay, here you adjust the parameters. So I would like to save all views, so all render views. Here you preset the image resolution, and then you will hit OK, and all the animation, maybe I can do it, and all the time frames will be stored as images. So now if I go back to my case, so let's check if I'm in the correct one. Yeah, I think it is. Yeah, test animation, and now you can see the images are rendered. So I will go back, and basically what you can do. Okay, I would like to stop it. Yeah. So, and what you can do. So if you adjust your view, etc., you can then have the animation something like this, in which I have compared, for example, these are the way we have done with different views. So for example, here we have the Q criterion with different values. Here we have the vorticity magnitude with different values, and you can nicely compare it. Basically, if you have two cases, so you can combine in the similar way the results from two different cases. So which I made, I think, here. So this is the visualization of the case with turbulence at the inlet. I don't know if this one, yeah. So this is the same, but with some artificial or random turbulence at the inlet, and at the end with some base scripting, but maybe it's not the purpose of this of today's webinar. But at the end, what you can have, I don't know if it will be properly visible, to have the animation of comparing all these visualization within a single window. So all of this can be done, and as you can see, there are almost unlimited way how to do the visualizations. And maybe what I would like to add, I have two more things maybe to show you. The first one, okay, what I didn't mention it. Okay, so all of these are connected with the visualizing the results, but also with ParaView you can also post-process the integral values. Yeah, so for example, you can simply compute the flow rate in any section of your domain you need. So just to show you quickly this, because time goes by pretty quickly. So let me, for example, open the Kaplan results again. And what I would like to show you are maybe two things in one shot. All right. So first of all, the ParaView also provides to script all the visualization, so you don't need to click anytime. You can create a script which you can run then automatically or from the console to create all the stuff you have defined, or when you are more familiar with the Python code, because the interface behind it is so-called ParaView Python, in which you can script all what we have basically done by clicking. And there is a nice tool which is called the tracing. So you can record everything you click, and it will be stored in the Python script, which can be loaded back or run in the console to do the same steps you done in the graphical user interface, or even you can modify it and create the visualization or any other evaluation automatically. So I will click here start trace just to show you how it works. And basically here you can choose which properties will be stored, if any property which will be touched by your click, or just the user defined or the property which will be affected by the clicking, or all of them. And here you can also add a show incremental trace. So anytime you change some property, it will show you the code which basically do these changes. So this is really nice for learning the ParaView Python interface and how it works. So I will keep this one. And now let's open one of your results. So I will open these Kaplan tutorial results. And as you can see, right after opening, you will see the code which needs to be done. And you have several lines which basically loads the results and load them into the scene we have here. So what I would like to show you is, for example, how to visualize or how to evaluate the flow rate at any intersection we have. So for example, we don't have available the flow rates, for example, for TCAE or whatever, or I would like to, for example, evaluate the integral values of the static pressure somewhere. So you can do it in this way. So I will create a general slice. So as an example, for example, I would like to see what is happening somewhere here in the elbow. So I will click apply. Perfect. So I have this section, and now I would like to know what is the flow rate here, for example. So I can apply the filter, which is called surface flow, I think. Yeah, here, surface flow. You can define the field from which this surface flow is evaluated. So it basically computes uh, for each phase on the intersection. It computes the normal component. It computes the surface area of that phase and the normal component of the velocity, and it multiplies it and basically integrate it. So by now we have evaluated, but the results are not in the data sense, but in the, let's say, just the values. And to visualize these values, you can open the spreadsheet view here, visualize the surface flow, which was done automatically, and now you can read the surface flow, so in SI units. So this is a cubic meters per second. And for example, you can adjust it. So for example, I would like to see just the surface flow, and I would like to save it into the CSV file, so flow rate. Okay, you can adjust the precision, and now you can see that on my disk we have there is a flow rate value with my surface flow for surface flow value. And for example, right now I am satisfied with this, so I can store this Python script, so I can save it. I will put into my uh, into my working directory into the project case, and flow rate, I will name it as flow rate. Okay, and what I can do now, so if anytime you have stored it, I will delete my flow rate. Or what we can do, for example, go what is happening inside. I don't want to go into much detail, but for example, here you have the file which is exporting the CSV, so you can rename it or put in any place. So my flow rate, for example, I can call it, click save, and now I can run the Python script directly from console. So I can run the command line. Now you need to locate the Paravi Python executable, which is within your TCAE installation. So my current version is this one. There is a bin directory, and there is somewhere pv Python. Then, just as working with the standard Python, if you would like to run it with the script, you just add the option -t and the name of the script, so flow rate. You will run it, and whenever it does everything what was defined or what is defined in the Python script, it will put your flow rate out. So you have here surface flow, and in this way you can manage, you can modify the script. So for example, if I would like now to uh, output all the values for flow rate for all my results, so we can go, for example, for ParaView documentation. So if I type ParaView documentation, so on the first item here we have the ParaView user guide, and somewhere here, for example, in the animation, you will find how to work with animation data in the script. So we have some example. So if you would like to go to the next, for example, to the next slide, to the next result, which I am here, right? No, sorry. It was here. So basically, if you go for any other slide, to go for the next, to go for the flow rate of the next point or the chosen point, so you can find a command using which you can do it. Or if you would like to iterate over all of them, so there is these functions which will return all the times available or computed basically in our sense. So I can go on my disk. I can, for example, go for a flow rate, and I can create. So I can load my scene, but my scene calls animation scene, I guess. Yeah, animation scene 1. So we can take all the times, and then in the loop, what I can do, so for t in times, I can do all these export, and for example, I can just create the name of the file based on the time value, and just to update the scene, which is somewhere here. So anytime we go for the next time frame, there is the command something like update. So I think we can go it in this way. I hope it will work. No, sorry, animation skin is not is the spreadsheet view. So for going for the next time, we need to update the results, and the last one, I need to go to the given time. So I think we did it here. So if you would like to go to the given time, so there is this command. So I will just copy it out. I will go to my, which is here, I guess. Yes. So I will put this command, so animation scene, and go to time. Now T, update the spreadsheet view and export the spreadsheet view to given file. So let's keep fingers crossed. I will run it again. Okay, invalid syntax. So I did it something wrong. Okay, I forgot one plus sign, and I hope I did everything in the correct way. Something is happening, and now you can see, yeah, it is exporting all the files. So here you will have the results for the first simulated point, here for the third, and in this way you can run it. You can do the, yeah, for example, flow rate evaluation in the automated way. In the similar way, but in more steps, what you can do is to, okay, maybe I will stop the tracing. On the surface, sorry, on the slice, sorry, I'm too fast. Discard and stop the trace, sorry, yeah. I don't need to record my trace anymore, but what I would like to show you is how to evaluate, for example, the static pressure average. So to do so, you can apply the integral variables or integrate variables, which is here. You can apply, and now the spreadsheet view is automatically visualized. And what I would like to do is to just go for the cell data, because I would like to have the area averaged value of the pressure or any quantity I have here. And basically this value is basically the sum of the pressure multiplied by the area for each face on the slice. What I mean is the basically surface fit edges. So for all this section, so it multiplies the pressure value times the area, and this is the value. And to have the area averaged value of the pressure, you need to just divide the value of pressure by the area, or K, or any other quantity. And in this way, you can evaluate the area averaged, or even if you compute the flow. So, and you create a new variable, pressure times the local flow. So then you can also have, for example, the flow rate average values and at any slide. And with combination with Python scripting, you can do it in the automated way. So this was also the example of the scripting, which is a really nice and powerful tool for automate the process. So if you have your project in which you need to have some special treatment in sense of evaluating something special, then you can click it in the Python, record it, do some modification with the script, and run it automatically after your simulation to get your advanced values automatically. And maybe still, I think I will take my last 5 minutes to show you the last thing what can be done in ParaView, last of many, but let me show you the last one. So what ParaView also offers is to, for example, combine two results and see, for example, differences of the pressure locally. So the difference of the pressure between two simulated cases. So for example, I will take this turbulence case. So if you load both of them, let me show you. So I will load the case without the turbulence at the inlet, let's say. So this one. And I would like to compare locally the magnitude of the velocity and the difference of the magnitude of the velocity for these two cases. This can be also done with ParaView, which is a nice advanced tool, which is not commonly known, but it's very, very nice. So what I will do is I will load both cases. So this is the case with no turbulence at the inlet, and this will be the case with the turbulence at the inlet. So turp in foam, yeah, this one. And now we can compare the pressure difference maybe everywhere. Let me check it. Oh, sorry. And okay. So what you can do is to create two variables to be compared with. So for example, let me compare the magnitude of the velocity. So I will name it velocity terp in, for example. I will define it as magnitude of the velocity. So this is my first field. Just to distinguish the name, because otherwise I will have two u fields, and the same for the other case. So for example, I name it in this way, velocity turbine. So velocity. Okay, I misspell it. Velocity turbine in this case. Sorry. And in this way, this is velocity no turbine, for example. Okay. And there is a filter which can combine both. Even you have non-conformal mesh, right? Even it's not the same mesh, but the same topology. You can create alphabetical, and this one is called resample with dataset. So it means it will take the source data from one case, so this calculator one, and will put on the destination mesh of the second case. And I would like to copy all the arrays which are available. So I think this could be it, I hope. But now I apply on the whole mesh, so I hope it will be done quickly. It seems that yes, I hope. Right. Now you have both values, so velocity for one case and velocity for the second case available on a single mesh or a single data. So what you can do now is to, for example, create a calculator, compute the field velocity difference, and take one, for example, velocity with no turbulence at the inlet, with the velocity with the turbulence at the inlet, and create the difference. And now you can visualize the difference of the velocities for these two cases, two different cases. So I will make a slice, for example, just to see just what is happening inside, and we can go to some later time, and you nicely see the difference, local difference between the velocity of one case and the second case. So this is nice tool for comparing, for example, the local pressure differences for two different cases where you, for example, just modified or optimized the blades and see the effect of this modification locally as a pressure difference or any other quantity difference, for example, velocity like here. So I think this is also a nice tool which ParaView offers, and there are many others. So do not be afraid of looking for new filters and new options in ParaView, because there are many of them, and which can be very handful and unique for you for visualizing what you need in your projects. All right, so I think from my side it's all what I would like to show you. Maybe I was a little bit more late than I expected, but I think we hadn't any deadline. So I think we can go back to Luboš if Luboš is still alive.
Yes, Radek, absolutely. I'm alive and I'm excited about what you have shown. It's really great. So yeah, thank you, Radek, for your part of the presentation. Thank you very much. And yep, let's go ahead in the webinar. Let's go ahead because time is running very quickly. So yep, what has been shown, and let's continue. Yep, in here. While you were
Perfect.
talking, I was playing here with our TCAE light tutorial formula here, but this is not exactly what I wanted to show because you have stolen me everything what I wanted to show. So your contribution was really extensive, Radek. So I think we can move ahead in the presentation. So expert on air has been already done. Yeah, thank you for it again. And now it's time for questions and answers. And this is going to be really interesting because as far as I know, we have only one question here. Believe it or not, there are a lot of people here, but we have only one question. And but nice one, really nice one. And it says, what are the best practices for critically analyze the results? Which is not obvious, but the second question makes it more precise. Also, how to identify what is good result and what is a bad one. Yeah, good question. So I was thinking about it a little bit because the question is here for a while. And it's, well, honestly, if you run some project, some engineering simulation for the first time, then there's no chance to realize or how to find out if the results are correct or not. It's impossible because it's data, and the data can be correct, data can be wrong, and it's really difficult to make any assessment what's correct or what's wrong. What helps? I mean, we can only tell what helps. Definitely, what helps is the practice, the experience. So if you have run, for example, a case many times, then you have you will, I would say, develop your assessment. You develop your eye for good results, for bad results. If you have, of course, some measurement data you can compare with, then it's again so much. I would say the life of an engineer is easier than if you have some data from measurement to compare. And at the end, I would say the data has to make sense. If they make sense, then you are on a good way. If they don't, then then perhaps there's something that can be improved. So yep. So well, it's this, and I would like to ask the audience if you quickly can. Still, we have some little time to you can ask your questions, and we will do our best. Otherwise, we can conclude. Radek, what do you think?
Yeah, this is a really interesting question, and it's pretty general one, right? So there are
Yeah.
several levels what you need to check, right? So
Maybe
you start
we can
with
discuss this. Yeah.
yes, uh, you can start with what is the expectation and what are the physical values of the results. And as I shown at the beginning, you can start with the residuals convergence with the integral values if they fit the expected range of efficiencies, pressure, and power. And then, okay, if it's in the expected range, then you need to go more inside. For example, to check the mesh quality for all the details. You need to check, for example, if some quantities are bounded or not, etc. So you need to go deeper and deeper if you need the analysis. If you would like to have the analysis in the sense of what is good and not good results. So sometimes if you do a benchmark and you would like to fit the measurement data, then you also need to think how the data was measured. So there are many unknowns and so many parameters that can
Yeah.
influence the results that you need to go from the yeah, the most important one, so the general values. And if you would like to achieve the accuracy less than 1% with the measurement, then you need to check all the detail including the mesh quality, local mesh refinement, numerics, etc. So
Yes.
yeah, so
Radek, this was a really good point. So we're engineers, right? So
mhm,
the things should make sense, right? So there
yes,
should be
definitely.
a lot of sense everywhere. But that cookbook you started was really good. So at first you have to be sure what you have set in the simulation, right? So
Mhm,
the simulation settings, it should be pretty I think clear and transparent to you. So there should not be like blind spots. I don't know what to set for this quantity, for this boundary condition. That would sound a little bit suspicious, right? But if you are certain about your boundary conditions, about your physical model, and simulation runs, and then it converges. So ideally the residuals should fall down. And
mhm,
if, for example, the everything is conserved, right? So if the
mhm,
flow rate or mass flow rate is conserved via a very interface, if the model losses are about around the expectations, then you are on a really good way to have good results. And then you can check, for example, what's the effect of your turbulence model, what's the mesh. Of course, mesh is very important. And so it's always an iteration process, right? But yeah. So well,
yeah,
it's
and in this way you can go
individual.
into more and more detail here to check what needs to be checked to achieve the given accuracy. So
And also, the devil is in the detail, Radek, right?
yeah,
We
yeah,
always
yeah,
say
yeah,
it in every
definitely.
project.
In every project.
But seriously, every project is
Mhm,
different. Every goals are different. Every budget in terms of effort, how much effort is going to be spent on the project is different, and etc. etc. So well. Let's get back to this. We
mhm,
really don't have any other questions, so I'll take it. Let's face it, let's conclude the webinar. So I would like to thank you. I would like to thank everyone for your attention. Still, you can come anytime back. We'll be happy to answer all your questions anytime, because it's our job and we have chosen it. It's our job and our pleasure. So let's come back anytime, and this could be it.
yeah, thank you very much for your patience, right? And looking forward for the next webinars.
Absolutely. Thank you, everyone, and bye bye for now.
Bye bye.